What's happening? What do you think it was? All right. Before I look at sharing stuff, connectivities. Okay, they are taking their own time. What is good, good, good. So, ping 172.16.10.1. So what's it from my faucet? 10 is customer B, right? So 8.1, not reachable. Okay, who's that? R1. Stuff all that. Seven is there. Oops, 8 is not there. From HB. Anything I have to activate here? Distributed connected. That's it, right? HB. 8 is not coming. What is the problem? So, I'll figure out. Eight is here. I think it is taking a little time. Yeah. Yeah. It took a little time. Oh, convergence in the startup, huh? Okay. So, good. Okay, 8 is pinging, and I think 6 is also in that group. 6 is confirm, guys. Is that the case? MPLS topology. Five is the customer A. So 578. So 5 is what I have to check. Okay, so I have the connectivity, and I will share these files. I'll just have to copy paste them. But what I want to do here is, before I do anything, I'll just go inside and say interface loopback 1, right? So to show IP interface, loopback 1 is what I'm using for the route ride. And to show run interface loopback 1, I made it as a point-to-point connection. So what I'll do is I will say no IP OSPF point to a network point-to-point. What is this? Oh. Uh-oh. This is weird. To show IP OSPF interface loopback 1, it has turned it to loopback type. Okay. And on R3, doesn't matter. Interface loopback 1, IP, no IP OSPF. Network type, and to show interface, network type is loopback. Okay, so with that, again, my data path should go down, right? So let us try to ping that 8.1. Yeah, so this is the issue we have, and so we have to configure it as OSPF network type. Point to point, right? That's what we said, and that is what we did. Now, what was told, and that is what I want to observe, is show IP route OSPF, and I can see the network 1.1 coming to me as a /32, and the same thing happens with this guy also, do show IP route OSPF, which is in the global routing table, right? 3.3, I'm getting it as a /32. Now, if you see it as a /32, the data plane will break. That's what we said. And why are we getting /32? Because the OSPF interface is a loopback interface. Okay. So show IP sev for that 3.3.1.1, let us say. And it is showing 3.3.1.1/32, whatever you are seeing in the OSPF database. Okay, show IP MPLS. Show MPLS. Forward table. This is the problem. Yeah. This is the problem with not able to establish the data path. In the MPLS forwarding table, which is the LFIB, okay, this is what is required, right? This is the LFIB. But okay, we'll get to that. This is the forwarding table, LFIB, which is having the network 3.3.1.0, which is not having the label. Okay, so in the LFIB, you are seeing the actual network, like the actual network address of that router. But whereas in the routing information base, you have this information. But what I am seeing is, I can see this also. This is also there. So if that is also there, then you should have the communication. Even though this is not having the label, I should still have the label.
But outgoing interface showing drop.
This is going to be the 3.3.1.0. This is the reason they gave. Okay, when I read the case, they gave this as the reason. Because this network will be there in the MPLS LFAB, routing table does not have that network, there will be no label for it. Okay, and therefore the packet will be dropped. This is the reason. Okay. This is the reason why you are not getting it, and therefore you need to have a routing information with /24. That's what they said.
This forwarding table, we can change it to /32.
Wait a minute. This is the reason why it is dropping. Okay. But this is the reason for dropping if this entry is not there. See that entry 3.3.1.1/32, that entry is also there, na?
No, it's already there.
So even though they said because LFIP will have the actual network information and MPLS will not, routing table does not have it, the packets will be dropped. Okay, this entry is justifying that. But this is also there, na? So even if I go with the longest length match, this will win. This should win. Okay. The solution is either take this out completely. Take this entry out. How do you take the country out? Simply go now IP OSPF point to point. By doing that, you will get only /24, and then you will have one entry. The other solution is configure the loopback itself as a 32. If you do that, this entry will be out. This entry will not be there. So if this entry is not there, then I will stick to this entry. Both of them are there. Then it is preferring this one. So you have only one of them. So first solution, like what we did, if I quickly go to R3 and interface loopback 1, IP OSPF network, point. If I do this here and go to R1, that entry is gone. Okay. And I'm supposed to get that entry back. Yeah, this one. So I have this entry now. Okay. So this is the entry which I now have. Because of this entry, I'm able to now route the packets properly because now I'm getting the proper network. Okay. So interestingly, 3311 it has created two labels. Why? That is very good. 3.3.1. It is using outgoing label, same outgoing label, but why did it create two? Out. 3.3.1. only one entry is there. And why did it have two? Local labels are created. Weird. Two different networks are there, so two local labels are created is okay. I understand that. But the question is why? Why this entry is still there is the question. Super weird. But let us verify the other part. So this is one thing. So I can simply come and say no, and then that network I am not advertising, therefore the routes will not be there. That 24 again goes back to drop. Okay. The other solution they gave is, okay, instead of configuring this as point to point, and right now if I say do show IP interface with backup, right? SPF interface. One, now it is again loop back type. The other thing they said is, okay, instead of doing this IP OSPF point to point, you can also give the IP as 3.0.1.1, 255.255.255. Keep only that entry. So my network type is still loop back. My network type is still loop back. However, now, if I look at my forwarding table, now this entry should go away. That entry should go away. No, not gone. But at the same time, let me also do it on this side and see if communication is happening first of all, because I never tested this side. So interface with that one. IP OSPF network. IP OSPF network, but then IP address, I will give it as 1.1.1.1, 255.255.255. So by doing that, and if it's gone, come back to that. Okay. So with that, first of all, I want to see if the data flow is happening. Okay, good. So data flow is happening. So the solution is correct. The second solution is instead of making them as point to point, you can also make them as a /32 IP address. So now let me see forwarding the forwarding table. Weird. If I am seeing it, if I have it from the routing table, I am using this one. I'm using this, but then the question will now be, why am I getting this one? When I made it point to point, I hope you guys are following, right? Guys? Am I talking to myself?
Yeah.
Okay, good. Okay. When I make it point to point, this entry should go away. When I give the /32, this entry should go away. But whatever I do, the entry is not going away, but it is taking the appropriate information. So now the routing entry will be 32 and it is picking that. If I get 24, my routing entry is 24, it is picking that. So whatever I have in the routing entry, it is trying to pick that. But the real question is, why is it getting this 32? Why is it getting 24 now? It is not supposed to get 24 at all. Who is giving it? I don't see it in my routing table, definitely. I definitely don't see it in my routing table. And where is it coming from? So OSP of database will have 3311, but that is just the type 1 LSA. Okay, let me see this. Here also I cannot see. Three dot 1.1. Here it is not showing. Here it is not showing 3.3.1.0. Why is it showing here? Oh, it's gone. It took that much time to converge, huh? Really? Okay. Okay, now anticipated result is coming. Okay. It took a while. Okay, now it is okay. Okay. Yeah, it took a while, guys. I mean, that's all. I was not patient enough. That's it. So that is the reason. So I will leave to the default. And by the way, if I check the connectivity from R7 to R5, that is having no problems. So it's either one or the other solution. Either you configure that loopback 1 as point to point. So if I take this example on this side, here I configure the loopback 1 3.3.1.1. Either you configure that as point to point, or you configure the interface itself as /32. And that doesn't even have to be same on all the PEs. So here we made this guy /32, this guy /32, and here we made him, we did not change here, right? So we made this as IP OSP of network type point to point. So yeah, but at least you get the point, right? So the point is that the data plane is broken because the LFIB is still maintaining a /24, and for that /24, because that /24 is what is the actual network information of this R3. In the routing table, because of the OSPF, you're getting a /32. There is an inconsistency and you're not able to go there. But the question still remains, guys. So that is, when this is a /24, when this is a /24, and you configured it as point to point, that is what was there from the beginning of our session, right? So still 32 is coming. 32 is still there. And so if 32 is still there, then it should ideally take the longest length match in the LFIP, but it did not take. So it still stick to the actual network. So that is still something unknown, but at least, yeah, we can figure out the point. Anyways, so why did I actually come here? I actually came here for running on.
So means to say that when we are using /32, so not required to define that as a point to point?
Exactly.
Okay.
What is the command? Anybody for the command types?
I think here no more will not take it. This is Cisco, so terminal links. Okay, you want to take?
I don't know. I want to just
take backup now. So terminal and 0, then so run.
Terminal?
Terminal length 0.
Oh, okay. That I think we should give it here.
Because no more will use in Juniper, I believe.
Oh, okay.
Okay. Yeah.
I'll just basically copy everything. Maybe from the host name. Yeah. Yeah. So if there is going to be this painstaking, I will do it in the lunch break. Yeah. So one quick moment. I'm going to start our session. VSS and VPC. Both of them are multi-chassis Ethernet technologies. Both of them are multi-chassis Ethernet, which basically implies you will have multiple switches
pair of switches, not multiple, to be very specific, 2 switches, which you can give an illusion of a single switch. Now, similar to a peer link, in VSS we used to have this, if I'm not wrong, that VSL link, okay, virtual switch link. We connected. Okay, now one is going to act like a primary and the other one is going to act like a secondary. When it comes to VSS, the most important differences are this. When it comes to VSS, there is only going to be one management plane and there is going to be only one control plane. Meaning, they are truly treated like a single switch. If I'm running OSPF, it will be running on the primary. Okay. The databases, however, are going to be synchronized with the secondary. Same thing. When management plane is going to be a single management plane. Now both of them will have a single console connectivity. Okay. I mean, management IP connectivity rather than console. Management IP connectivity. There will be only one. So you're truly treating that as a single device. And that is the reason why it is not that ugly. Okay. It was fine. It was okay to run VSS and it was still stable. It was good enough. Because I did not have any complications of multiple control planes, multiple management planes. That was the real problem with VPC. Okay, so VSS had one management plane and one control plane. There is another important technical difference. VSS can be used for layer 3 and layer 2 port channels. That means I can configure this as a switched port and I can have a regular port channel. I can also have no switch port, configure this with a IP address, and I can have this as a layer 3 port channel also, a layer 3 virtual port channel. I can create that. But whereas when it comes to VPC, there is a separate management plane and separate control plane and only L2. You cannot have an L3 port channel. You cannot have it in VPC. It's purely L2 related. Okay, so that is at another thing, technically speaking. Okay, and what else should I give as the differences? I just thought of something and I forgot. I just thought of saying something for this. Anyways, yeah. So, yes, and again, one very miscellaneous thing, this is for Catalyst, this is for Nexus, so that is another thing you should remember. The reason, I was for a while thinking, okay, if this is the real problem, separate management, separate control planes, so why did they do that? I mean, why did they have to do this separate management and control planes? Because this is the one which is losing the stability. When it's having one single management plane, there is no error. I mean, there is less error. I don't want to say no error, but there will be less error because only one management. I will go there and I will configure it. I will put these 2 ports in the same VPC. I will configure the same settings. All of that I will do it, in one shot, one go, almost like an extended switch. Why did they have this separate management in the control plane was my doubt for a while, for a very long time. The answer to that is these Nexus switches, not all of them, but most predominantly the 5Ks, they were also used as storage switches. Okay, as I said yesterday I think, 5Ks, now 9Ks, we can have these ports which can be configured as FC ports, like native FC ports. I can configure that. For fiber channel, for this storage switches, the protocols that are going to run are separate protocols. And for storage, the preference of the storage is always to keep things separate, isolated. For networking, we always want to have crisscross connections, right? This is how we prefer to have our connections. But whereas when it comes to storage, they always wanted to have a separate, physically separate sites. They also need redundancy, but their design from the beginning is always going to be separate connections. So they have their own protocols that are going to run. Now, when you have separate physical connections, and if they have to be separate protocols, I cannot say I will have a single control plane. That is the real reason. It is not networking, it's not VPC technology, it is not the Nexus box that is giving me the constraint. The constraint is because I am using Nexus boxes for this particular VPC purpose, and mostly the Nexus boxes can also be used for storage. I wanted that separation, I wanted that compatibility. I should be still able to use it for storage, and I also want to do the VPC. Because of that aspect, they had to have separate control planes and separate management. And for that, you see all those possible failure scenarios, and certain failure scenarios yesterday we saw. You just can't avoid. You just can't avoid the split brain. You just can't avoid the convergence or reconvergence issues. It's just that. Okay. So yeah. So that is the differences between your VSS and VPC. Okay.
So once we create configured VSS, so all the data and control traffic will be forwarded from the primary one.
Yeah. That is the one I wanted to say. Yes.
Okay.
So control plane and management plane are only one, but for the data plane, they are still active. Yes. So from a data plane perspective, they are still active. Come on, that is the whole purpose, right? So why do I need this two switches acting like a single switch? Device redundancy. Okay. But for device redundancy, I should not lose the capacity of my port channel, right? So for that, yes, you need to have the data planes active. It's not like primary is the only one that will do. Now primary will have a significance. One second. Primary will have a significance because now the control plane is acting on the primary. Now I go into the primary box for the configuration purpose. Both the control plane database is synchronized between them, and the management plane, which is configuration, is also synchronized between them through the primary. Yes, please. Yeah.
So, Kalyan, if there is a switch, like in this topology, there is a switch which is connected to VPC switches, and there are two routers. One is connected to switch 1 and another router is connected to switch 2. But the only one router is active at a time, means another is a standby secondary router.
In VSS or VPC?
VPC, I'm talking about VPC.
Okay.
See, yeah, the switch 1, switch 2, and there are two routers. No, two different routers. Yeah, one is connected here and one is connected to there. The primary is the active router is router 1. There is an internet router and that is active, and router 2 is a standby, the secondary one. And there is a.
I mean, you mean to say HSRP is running on this, is it?
We can say, or we can say EBGP, EBGP or IBGP, means both are internet router.
I don't care, but why did you say active or standby? That is important for
active me. And means one internet circuit is active, another will become active only when one router 1 goes down.
You are telling me in English. Tell me technically, I'm asking. Okay, how did you make this active? How do the systems know that it is active? Either you are running HSRP or something.
Yeah.
Or there must be some routing protocol running between them so that this is made a better path. What did you do? You are telling me this is active. What did you do for that?
Yeah, we can run OSPF actually as a LAN protocol and for EBG for the internet route.
So you mean to say you are running a routing protocol between R1, R2, switch 1, switch 2, right?
Yeah, OSPF.
Okay. So through the PBR, you have made that the primary link.
Yes.
Okay, fine. Yeah, now tell me.
We have created a route map and associated with the router one so that it is primary. So now if server down the line there is a server, and if this server process means any traffic towards the internet, so the primary will forward the traffic, or means how what is the traffic flow?
Once the packet comes from here to here, right? So the gateway is sitting here. So let us give some numbers. 10.5 is here. VIP address, not VIP address. No? You have this, what is that? Whatever. How do I put it? 2.5, let us say. 2.6, let us say. And let us give another number here. Maybe I have another connection like this. I should have, right? Because switch
peer keep alive.
Not peer keep alive. No. For my routing, how will switch 1, switch 2 participate with R1, R2? If they are not physically reachable, how will that have a backup route? Right?
But
so maybe I'll have 3.1, 3.2. Right?
Okay.
I need to have routing adjacency because you said OSPF I'm running, right?
Yeah, but there is a peer link as well between the switches.
I mean, that is for my VPC. That is for my VPC purposes. Okay. I need my routing. Okay. So now you have to answer the question, where is the gateway? For this, I must have a gateway, no? Where is the gateway?
Gateway is my router actually. Fine.
Then how can you?
No, sorry. Gateway. Actually, we created a VLANs of the switch 1 or switch 2. Then we
so
will
the gateway. So you mean the HSRP is running on this? The gateways are sitting here.
Yes.
Okay, got it. So 10.1 is the gateway. So your question? How will I use this as a primary? Right?
Yeah, means from VPC perspective, I just want to know the flow. Means will it sometimes forward the traffic to the switch 1 and then switch 2? Then switch 2 will forward the traffic to the switch 1 and then router 1. We can use both link active in this scenario because we have VPC.
Very good. That's the key point. Okay, so for the VPC, when you run HSRP, even though output says active standby, both are going to be active. So if you said R1 is the primary because of your PBR, when the packets come to switch 1, because there's no guarantee, right? Server 1 can go in this direction or in this direction. It's a port channel for it. If it comes to switch 1, it is going to send it directly, no big deal. But if it comes to switch 2, in that case, it uses the routed port because 2.5 is the next hop for the internet routes. It will use the routed port. It will send the traffic on this, not the peer link, but it will send the traffic on this.
But Kalyan, what I have observed in my real time scenario actually, sometimes I have observed MAC address on the switch 1. On the other second, the MAC address is getting learned on the switch 2. Means
MAC address of server 1? MAC address of server 1?
Yes. Means it's for... Okay. So, sometimes... Please go ahead.
Yeah. When it comes to server 1, on S1 and S2, you must be learning, you must be seeing the MAC address on both the switches, not on one switch. You should be seeing it on both the switches. The reason is, wherever it goes, once it reaches one of the switches, it will be synchronized with the other switch. So you must be learning it on both.
Yeah, but what it shows actually, when it forwards the traffic, it shows it is directly connected to switch 1 actually. and the other time it shows we are getting this MAC address. Yeah,
Wait a minute. Wait a minute. How did you say the 10.5? Let us say the MAC address is 5A is connected to switch 1. How did you say that? What is
because VPC, because there is a VPC, and suppose
so it is showing it as port channel 5, for example, right?
Yeah.
That is what it is showing. Okay. So that is what you meant by I am able to see it in see it as directly connected. Okay.
Yeah, directly connected means port channel. I am getting the MAC address through this port channel, and the other second means other next 1 second. I see that MAC address is landing via peer link. There is also a port channel 10 means peer link. So I'm getting this same MAC address via peer link.
It is possible. This scenario is possible if you decided to use the peer link as a layer 3 interface as well, which is not recommended by Cisco, but you can do that.
Peer link
can also be used for the layer 3 traffic.
Yeah, but peer link I see as a L2 port channel.
That is what. Yes. Okay. This is not a recommended thing to do. You have to do some config, some knobs you have to change. If you did this, trying to use the peer link for my routed port communication, if you did that, in that case, you are going to send the traffic in this link. So what you are having is not a routed port. Okay, what you are having is not a routed port. What you are having is on the peer link, you would configure a trunk. Remember, it's not a routed port per se. You are configuring a trunk, and through this, you are sending your layer 3 traffic. So you are using all these SVIs to form the neighbor adjacencies. I'm 100% sure that is what you are doing. Instead of configuring the routed ports, which is supposed to be an ideal thing to do, you are configuring trunk port. So through the SVIs, you are forming adjacencies.
Yeah, we have means whatever we have VLAN, we have allowed through the trunk port, allowed the VLANs on the peer.
Exactly. And the more important thing is the adjacency. Adjacency you are forming with the SVIs, not the routed port. You have interface VLAN 10, interface VLAN 20, all of them are here, right? Here and here. Through the interface VLAN 10, you are forming adjacency, not a routed port.
Although actually we have only a certain SVIs on the switches, and all the gateways are configured on the firewall, and there are 2 firewall which is connected to switch 1, another firewall is connected to switch 2. But my purpose was to just confirm that there is a server, it may forward the traffic, means sometimes switch 1, another time switch 2. So both link, and there is no any issue.
Okay. I did not understand the last part. Is it a statement or a question or?
Means it was a query. I have seen in my real time scenario, there is no any negative impact, but I was curious to know.
Now you got the answer?
Yeah, through the, I got the answer.
Yeah,
and could you please let me know the peer gateway, means which we configure the command in the VPC domain, so that
this whole scenario which we were talking, I'm just curious asking, is this whole scenario related to any peer gateway? Yes or no?
See, actually, I read somewhere
yes
that
or no? Is our scenario which we were talking, is it related to the command peer gateway? Yes or no? Make a guess.
I think yes.
No, absolutely no.
So without this command,
you enable this command or not enable this command, the behavior is going to be the same.
Okay, so in which condition we should execute this command, peer gateway?
Only in one case. You have your 10.2 here, 10.3 here. 2 has got a MAC address of 2A, 3 has got a MAC address of 3A. You are using a VIP address 10.1, which has a virtual MAC address of 1A. For some weirdo reason, there is some old storage device which is contacting the gateway 10.1 with the MAC address of 2A, for example. Not the 1A, which is supposed to be the case, right? If there is a remote corner scenario where the storage device is directly contacting the MAC address of the interface rather than the virtual MAC address of the gateway, if the packet goes to S2, it will be sent on the peer link to S1.
Okay. Okay, got it.
With the peer gateway command, what you are telling is, see, even if the packets are coming for the MAC address of your other peer, you respond, you process them. That's what you are telling with peer gateway. I will repeat myself again here. The reason why you are seeing sometimes the server coming through the port channel 5, sometimes the server coming through the peer link is because you have configured this with a trunk allowing all the layer 3 traffic as well. You have done that instead of, this is not a good practice. The good practice Cisco recommends is to have a separate link for the trunk so that your layer 3 traffic can go in this direction and you do not allow those VLANs or whatever on the peer link. That is the good practice. However, port density budgets, unnecessary link, you don't want it. Therefore, you in your environment have allowed the same peer link to use this configured as trunk to use that peer link for the L3 traffic. That's why when the traffic is coming here, it is going directly and you're learning it on port channel 5. And when the traffic comes here, if it has to reach the primary, because that's your goal, there is no other way to go because you did not provide me the connection there. So I will go through the peer link. So when the frames go in this port channel, in this link, I will learn from here. And when I learn it from here, when I get the frame from here, I will learn it from the peer link. That is what is happening. Okay.
And Kalyan, one last query actually. If both routers were active, so whenever switch 1 will get the traffic, it will forward to the router. And if switch 2 get the packets from the server, it will forward to the another router.
Exactly. Exactly. Okay.
In that case, we utilize both of links and both of...
Again, see this. When you have a connection like this, how do you say that these are all both active? So keep that point in mind. Okay, so in your
active means you can say load sharing.
That is what. In your routing table, please be careful about that. Do you have both the routes in the routing table for the internet? In that case, some of the flows will go directly, some of the flows still will go through the peer link because of this trunk configuration layer 3 traffic center. The ideal thing to do is to make this connection possible. Just do this. Unnecessarily, you don't interfere with the peer link. This peer link will now be used only for backup purpose. The best thing to do is this. Even better is add another trunk port. Now that is asking too much from the client, right? Okay, so it's almost like they will think, oh, don't do anything to my switches.
Sorry to interrupt you, but in this case, actually now we have connected router 1 to router switch 2 as well.
Yes.
We have another link. So switch 2 can forward the traffic to router 1 itself.
Yeah, exactly. Nah. So now I will have both the paths. Now you can very comfortably put this R1 as the primary. Absolutely no problem. You will send it here. Even if you are doing load balancing, no problem, because I send half the traffic on this, half the traffic on this. Directly I will send. Very smooth ride.
in that condition, I would not get the MAC address via peer link in that condition.
Exactly. Exactly.
Which will get forward the traffic itself to the router.
That's it.
Oh,
Simple.
okay. Yeah. Now I'm okay. Thank you.
So Kalyan, peer link will be the same. That is heartbeat link, which is for initiating the VPC neighbor.
That is the keep alive link. Na? Heartbeat link is the keep alive.
Okay.
Okay.
Then I think we need to avoid using this as a trunk. I mean, VPC, peer link.
Absolutely. Peer link, when you read a document of VPC, every other 10 pages once, they will say, don't use the peer link for data traffic. Okay, so try your best to avoid it completely. Only for synchronization of the databases and multicast traffics, you can use it. You cannot avoid that. But other than that, try to avoid it as much as possible.
Right.
Alrighty. Okay, so, one second. Yes. So now let us get into the fabric path. Kind of the future of networking started kind of with this thing. I don't want to give too much credit to fabric path and Cisco, but kind of it started there. So what is fabric path? What is the goal? What is the need for it? Very simple goal. Eliminate STP. Like terminate STP. Just don't ever use STP. That is the goal of fabric path. Okay. I must tell you, fabric path is inspired. Yeah, that's the better word. Is inspired from a technology which today, tomorrow, day after tomorrow, I don't know when, hopefully one day will come up and become a standard. It is inspired by the technology called Trill. What is the full form of this? It's a very fancy word. Ton of redundant interlink something. Okay. So Trill, that is the Ethernet, and a kind of a new Ethernet standard. Okay. It is, trying to come for like what, last 10 years or so, or even a little more. But if Trill comes, like if the Trill becomes a standard and every Ethernet card will support this technology of Trill, like right now you're sending Ethernet frames, right? NIC cards will send Ethernet frames. So if NIC cards are compatible with Trill, pretty much switching will become almost an automatic process. It becomes an automated process. Okay. So don't worry about Trill, but whatever I'm going to discuss in fabric path has a lot of relevance to this open standard technology called Trill. But our focus is on fabric path. What is it and why do I need it and what's the approach in communication? See, when we see the evolution, right, we had multiple links, but only one link was used because loops are there. STP was developed. And then we said, okay, we will use per VLAN STP, and then we will create different trees, different topologies for different VLANs, so that I can start using multiple links simultaneously. That was the next level. Next level, they said, okay, 200 VLANs are there, but there are only 2 uplinks, so I don't need 200 instances. So then they cut down the instances. So MSTP came. MSTP said, okay, you can run 2 instances, map the 100 VLANs in one instance, another 100 VLANs in another instance. So you can use 2 links simultaneously. However, for one instance, that one link can be used. I cannot use both for that one instance, one VNAND instance or one MST instance. I cannot use multiple at the same time. And so came Ether channel. So fine, I will create a logical port channel. So your STP or your data plane will think that it is a single port channel, single link, and the data will come to that port channel or BPDU will be sent to that port channel. Within the port channel, I will only do load balancing, like per flow load balance, depending on the hashing I do, depending on the criteria I select. So now I can start to get excess bandwidth on a per VLAN basis or a per MSTP instance basis. But still we cannot avoid STP, right? Because link redundancy is there, higher bandwidth is coming, but device redundancy is missing. So we went on with VPC. We went on with VPC saying, okay, instead of connecting it to a single switch, I will connect it to a pair of switches. I will give you an illusion. I'll give you an illusion that it is a single switch by manipulating the LACP ID. They both will send same system ID. They will send the same priority. So the switch or the server will think it is a single switch. So now I get link redundancy, I get higher bandwidth, and I can also get the device redundancy. So that was the next level. However, that is it. That means that is it. I cannot have another switch. I cannot randomly connect the way I want. So if I have a system here trying to communicate to another system here, I cannot just like that say, okay, I will have another switch. Can I connect it like this? Can I use all the links? I cannot say that. I cannot use all the links. It is always supposed to be a triangle. Yes, this I can use it as a VPC. I can do that. Yes, I can configure a port channel here. Yes, I can do that. But I cannot come and say, can I use this link also? How about if I have another link here? Can I use these links? Like I connect it like this, left, right, and center, all of these links. Can I use all of these links in order to send my traffic from switch 1 to switch 4, for example? Can I use all of them? With VPC, no, it is not possible to do that. So this is where they said, okay, let us try to build a technology that will allow me, number one, to provide arbitrary connections. I don't care where they are. I don't care how I want to connect. I should be given the flexibility to connect the way I want. You cannot say only 2 routers or 2 switches. You just don't put a constraint. You just allow me to have arbitrary constraints. Number one. Number two, I don't want to have any loops going on. Because you have given me arbitrary connections, so I can also have a connection like this, I can have a connection like this. Loops are very easy to form, and I don't want those loops to be occurring. So how do you achieve that? How do you achieve such a thing? And the answer to that is, I love this statement. In the last 7 years, I am loving this more and more. The way you do that is routing the frame. That's it. That's it. All that you do is route to the frame. See, if I did not say that these are switches, instead, if I said these are routers, same, physically the same topology, If I say that these are routers, and if I say 10.5 wants to communicate to 20.5, and if I have multiple paths like this, can I do load balancing on all the 4 links? Can I do that? Yes or no? Answer please. Absolutely yes. Very good, okay. Absolutely yes. I mean, I had never had an issue. My routing was always from day one, whether it is static route, default route, or dynamic routing protocol, I was always able to do routing. I will always be able to do load balancing on a per flow or a per packet basis. Why can't I do that here? Why can't I do that with the switches? I can use the same thing. Logically, technically, I am not doing any different. I was always routing the frames, routing the packets. My packets are always getting routed. I was always able to use the way I want. I was always having redundancies the way I want. Let us do the same thing for the frame. That is the whole idea. Okay, we are discussing fabric path today. Monday we will be discussing VXLAN. Someday you will be discussing Lisp. And tomorrow maybe we will be discussing, today itself, we may be discussing OTV. Any technology coming up, you may learn in the future, observe, it is all going to be routing the frames only. Ultimately, the goal is to route the frame. In the WAN also, you have things like SD-WAN, you have segment routing, you have MPLS TE does not make sense, but segment routing is there. Lisp, I can use it in the WAN. Any of these new technologies, the final goal was very simple. You just route the frame. Frame is creating loops, switches could not do that loop avoidance, so STP is brought. Packets can always be loop avoided. I was always able to load balance, so just route the frame. That's it. So any solution which we discuss from here on is routing the frames. Somehow, one way or the other, it is going to route the frames. Okay, how does it happen in fabric path now? Here is the thing. Switch 1, switch 2, switch 3, switch 4. When 10.5 wants to communicate with 10.6, maybe 5A is the MAC address of this, 6A is the MAC address of this. When you send the frame to the switch, when you're sending the frame to the frame is learned in the switch MAC address table, just like a regular stuff, right? It will learn the source MAC address. It will learn the source MAC address, which is 5A, and it will learn the port number 1/2. It will learn it and then see what happens. You have your original Ethernet frame. This is the original Ethernet frame, which contains the source MAC address of 5A, destination MAC address of 6A. What it does is, in fabric path, what it does is, it is going to encapsulate this with the source switch and the destination switch. In this case, switch 1 will be the source of it. Switch 2, in this case, switch 4 will be the destination. So what happens when the frame is received by switch 1, it learns the MAC address of the source and the port number, just like a regular switching. We call it classical switching now. It will learn it and it will route that packet. You don't officially call this as a packet. We call it as a fabric path frame. We call it like this. But what it is doing is, it is going to add the source switch and the destination switch. And in this fabric, the connection between the switches and the access switches here, it is going to route to switch 4. It is going to route that frame, the inner frame, to switch 4. And once the frame is received by switch 4 is going to decapsulate this and send the original frame to the destination system. But here there is one thing you should know. When you are sending the frame, this may be coming from VLAN number 10, for example. So anytime I am sending my original Ethernet frame, I will also add the VLAN tag to it, so that the other end switch will know that it is coming from VLAN 10. So in case there is a system I don't know where it is, I will send it to all the ports in that VLAN 10. So here what I am doing, I'm getting the frame like a regular classical frame you get, and I learn like a regular classical frame. And in the fabric, I am going to route it, not based on the destination MAC addresses, that's what switching does, but now I'm going to route based on the destination switch, where that switch is. That is what I do with fabric path. And that is the way routing is done for the frame in fabric path. Okay. Okay. But there was a lot of questions unanswered. First question, many people ask, how will switch 1 know that 10.6 is connected to switch 4? How will switch 1 know? That's a very immediate question people will ask. But I have a even fundamental question. Before knowing how switch 1 knows 10.6 is connected to switch 4, my fundamental question is, how does switch 1 know that there is switch 2, there is switch 3, there is switch 4, there is switch 101, there is switch 102, there is switch 103? How will the switch 1 know that these are all the switches in the setup? Right? First, I should know that. Every switch should know that there are other switches in the topology. That is my fundamental question. Then the question will come, okay, how will the switch 1 know that 10.6 is connected to switch 4? That is the second question. First question is, how does switch 1 know that these are all the switches? That is the first fundamental thing. Second, so if I have to write the questions, how each switch knows the topology. How will they know who is where, how to reach them? How do you know? 1. 2. Okay, switch 1 will use switch, source will be switch 1, I said. Destination will be switch 4, I said. Okay. What will be the switch identification? What will be the switch identification? Will it use an IP address? Will it use some MAC address? Will it use something else? What? If I have to have an identification, what? What is that identification? Another question. Okay. Another question. Somehow, I don't know how, but okay, let me write it down. The third question I said, right? The third question is, how MAC to switch mapping is made. Let me write it down. That means, how will switch 1 know that 10.6 or 6A is connected to switch 4? How will it know? So that's the question which comes third. Okay, many people ask this as the first question. How will it know? Before that, I have to answer these two. Okay, let us know. Let us somehow it went and somehow it found. But When 10.5, 5A, wants to communicate with 10.6, 6A for the first time, 5A does not know what is the MAC address of 10.6. It does not know, right? You may call any technology whatever you want, but from a systems perspective, I'm just doing my job of LAN communication, that's all. So when I want to talk to 10.6, which is in my network, I will send an ARP broadcast request. So when I send the ARP broadcast request, it's a broadcast message. Where will it go? I don't know where 10.6 is. It may be on any switch. So if I have to send it on all the ports to all the switches, I mean, come on, packet will come here to here to here to here to here and then loops back. Mess. So in one word, how to handle bum traffic. What is bum traffic? Very funny word. Broadcast unknown unicast, not unicast, unknown unicast, and multicast. What if I have to send traffic to everybody? Will I use all the links? If I say I will use all the links, then the other switch should also use all the links, and then other switch, then everybody will use all the links and loop is created. So how will I handle that bum traffic? So these are all the questions I need to answer. As a end result, right? As an end result, this is what happens. Frame comes in, switch 1 will send it to the destination switch. The inside of the fabric will route based on the switch, not on the actual destination. And once it reaches the destination, it will decapsulate the fabric path frame and send the Ethernet frame to the respective destination. That's the end result. So now we have to answer each of these one by one. And the answers are very simple and straightforward. The first thing, what will be the identity for the switch? What is the identity for the switch? Nothing. You will have, when I say nothing, it's not nothing, okay? It's a switch ID. Every switch will be given a ID. It is not complicated. It's a 12-bit number, so you can get 4096 IDs. It's just an integer value. So every switch will, or rather let me rephrase it, every switch must have a switch ID. Okay. Should I configure it manually, or will it automatically be taken, or how is it? Here is the thing. You are going to run a protocol called Ddap. All that you do from a configuration perspective is you are going to configure all these ports as fabric path ports, right? There are literally, no jokes, literally there are 2 commands you should give. That's it. Fabric path will work. Just like that. You don't have to touch anything there. Such a beautiful thing for configuration. Okay, you don't have to do anything. Just give 2 commands. First command I'm telling you is to activate fabric path on these ports. Second command I will tell you last. Okay. So once you do that, there is a protocol called Ddap, Dynamic Resource Allocation Protocol. What it does is almost like a DHCP. Every switch will pick randomly within the range. It will pick one ID. It will pick one ID and it will request everybody on the fabric path links. It will send a broadcast to everybody saying, I am taking this ID. Does anybody have it? It's going to send a request, almost like a GR, but here it's going to be Ddap. So it will identify if the switch ID is unique, and then it will reserve itself. Next switch comes up, it will randomly pick an ID. Oh, the same ID which switch one took. So when it makes a request, switch one says, I already have the ID. And switch two will again randomly pick one ID. So you really don't have to touch anything. Automatically the switch ID will be assigned to each switch. Each of them will take a switch ID. However, in real time, we want to assign the switch ID. So you can assign dynamically using Ddap, which will automatically take the IP or take the switch ID, or you can also assign statically. Manually you can assign. You have control now. You have easy identification. Okay, switch one is ID number 1 or 101, 102, 3, 4, 5, 6, whatever. So first thing, you have a control protocol called Ddap that can run. Use it to get the switch ID dynamically. You can also configure the switch ID manually in real world. Configuring manually is what we prefer to do for ease of identification. Okay, good. The first question is answered. How will the switches have an ID? And the answer is using an integer number called switch ID. Then this question. Okay, now each one has a switch ID. How do they know each other? Like, how does switch one know that I can reach switch 4? Remember, Ddap told me what are all the IDs. But if I don't use Ddap, then statically I give. In either cases, I don't still know the topology. I still don't know that from S1 to S4, I can go on port 25, 26. If another port is added tomorrow, 23, I don't know that I can reach switch 4 from all these 3 ports. I still don't know that. I still don't know the topology of it. So the next question is, how do I know the topology? Tomorrow, if I want to route any fabric path frames to any of the switches, I should know how to reach there. And the answer to that is ISIS is activated on the fabric path ports using ISIS. Yup. ISIS is the routing protocol that will be activated. Again, you don't have to touch a link. Nothing you should do. It will automatically do this. So the moment you enable fabric path, ISIS will be activated on this. Remember, we had a discussion on ISIS when we talked about MPBGP. So I had a very specific reason, and this is the reason. ISIS is capable of not just transmitting IPv4 routes. It is capable of transmitting anything you want. It can transmit MAC addresses. It can transmit, again, nobody developed it, but if you wanted, it can transmit neighbor details like CDP. It can transmit, I don't know, like SNMP, it can transmit information about your device. It can transmit anything by adding new TLV fields. By simply adding the new TLV fields, you can advertise anything you want. With regards to fabric path, what they did is they said ISIS to advertise the switch IDs. So the job of ISIS is to advertise, first of all, if I have to go step by step, to form neighbor adjacencies with all the neighbors to exchange switch IDs. Instead of a routing table, instead of IPv4 routes, it now exchanges the switch IDs to build topology databases and to build routing tables. Almost for the first time, you are hearing that in order to reach 3.0, I have serial 0, serial 1. Instead of seeing things like this, for the first time you are going to see, to reach switch ID number 4, there are two paths, 25 and 26. This is what you will see in the ISIS routing table, quote unquote routing table. This is what you will see. Tomorrow, if I want to transfer data from switch 1 to switch 4, I will do load balancing. One flow, I will send it on 25. One flow, I will send it on 26. When it reaches switch 101, if it has a direct connection, fine. In my routing table, ISIS routing table, to switch ID 4, I will have a path of 35, for example. Now I will route the packet to this. When the packet comes to switch 102, it will have in its routing table to switch ID 4, path of maybe 36. Now load balance is happening. Routing of the frames, the fabric path frame, is what I am doing now. You don't even touch it. You just give this command fabric path, enable it. Everything is happening automatically. Can I tweak them like I tweak my ISIS? Can I change the cost? Can I change any of those settings? Yes, absolutely. Yes, you can do it. But there's no reason why you want to do it. But yes, you can do it. So now routing is happening. I mean, so simple the solutions are. Right? So these are all the things it does. It will build the routing tables and allow for ECMP. And the last thing that it does is it is used to build multi-destination trees, MDTs, multi-destination trees. This is very, very, very important for ISIS. And the reason why they chose link state protocols is because link state protocols are the only ones which have the topology view. EIGRP, BGP, they don't have topology views. We discussed that long time back, right? So ISIS is chosen because it has the new TLVPs. It can be expanded. It does not need an IP address to actually form neighbor adjacencies. So that's the reason why they took it. So multi-destination trees are built, which is very, very important. Why they are important? Coming up. But let me tell you what these multi-destination trees are. So what happens is, once the topology view is built, once the switch 1 knows that there are 3 neighbors to it, it knows how to reach the neighbors, it knows how to reach the others in the topology, then what happens, one of the switches is going to be the root, like the centric point. We call it root. So in this example, if I assume everybody is connected to everybody else directly, what happens is it is going to create this multi-destination trees. For example, I will say switch 101 is the root. So with switch 101 as the root, I'm just creating one multi-destination tree. Again, I hope you remember the topology. 101, 102, 103 are not connected, but switch 1, 2, 3, 4 are connected directly to 101, 102, and 103. So with that in mind, I will build from 101, let's say I go to switch 1, I go to switch 2, maybe from switch 2 I go to switch 102, from here I go to switch 103, And from 103, maybe I will connect it to switch 4. This is one tree. Everybody is involved in this. 101, 102, 103, switch 1, 2, 3 is missing. Huh? So maybe I will connect like this. Switch 3, I'll call it, switch 4, I'll call it. So everybody will be involved in this tree. This is one tree. This way, when it comes to fabric path, it will create 2 trees like this. It can create more, but with fabric path, it will create 2 trees. Now, I'm taking the example of the same root switch. Same root. Okay. The reason why I'm taking the same root is I just wanted to prove the point. Because it's the same root doesn't mean I need to have the same tree. Maybe I have a setup like this. Now this time I will say switch 102, switch 103, and maybe from 102, I will have a connection to switch. All are covered, right? So that's fine. I'll have it like this. Switch 1, 2, 3. 4 is there, right? Yeah. I'll connect it to switch. See, what I want you to observe from this is I am building a loop-free multi-destination tree. That is what I am doing in this process. I am building a loop-free multi-destination tree, all done automatically by ISIS, only because of the fact that it knows the topology view. If you look at this setup, it almost looks like STP root switch selection process. It's almost looking like that. But instead of STP doing it, it is now ISIS building these multi-destination trees. As I said, in fabric path, you will build 2 trees. Each of these trees is given a ID. They call it as F tag. Okay. F tag, maybe in this case, F tag 1 and F tag 2. So 2 multi-destination trees will be built. So this is another function. So there are few functions ISIS is doing. Number 1, forming adjacency with the neighbors. Number 2, exchanging the topology view so that everybody knows everybody else. And then finding the routing entries to reach those other switches and allowing for ECMP. And finally, multi-destination trees are built by ISIS. All of that happening automatically. So that is what answers this question. Okay. Now, I want to understand how this happens, how bump traffic is handled. Because if I look at my initial communication, when 10.5 wants to communicate to 10.6, 5A will first send an ARP broadcast. So now I want to understand the data flow. Now in that process, I am going to basically answer both these questions. How will you handle bump traffic? Because that's the first thing that comes, ARP broadcast in this example. And eventually during the data process, data packet flow, we will also learn how MAC to switch mapping is done. So let us talk about that. So here is the thing. Once I get a frame, this time 10.5 wants to communicate to 10.6. First time 5A is sending an ARP broadcast. So once I get a frame, I am getting it from this classical Ethernet, right? So I will simply learn the source MAC address and the source port number. No rules, no conditions. I will just learn it. That's what I do. That's what I did for decades. So I do the same thing. Now I see this is a broadcast message, right? Because it's 12Fs. Our broadcast is coming. Now, because it is a broadcast message, what this switch 1 will do is, the switch 1 will pick one of the multi-destination trees. It will pick one of the multi-destination trees. So in this particular example, it is going to say, let us say it is going to pick on this one. It is picking on the first tree. So what it does is, you have your original Ethernet frame, original broadcast Ethernet frame, right? It's a 12F thing. Now what I do is, when I'm sending it, I will send it with my ID. So switch 1 ID, my switch ID, and the destination, this is the source, the destination is going to be 12Fs. You said destination will be outer switch ID, right? Yes. If it is a unicast message, it will be the outer switch ID. But because it's a broadcast message, I will send with 12Fs. That will be my destination. And along with this, I will also add the F tag. Okay, which F tag am I using? So this is something that the source switch is going to decide. So it decided that it has to use F tag 1. So what it does is, okay, according to this F tag 1, according to this multi-destination tree, where am I? I am right here. In the tree, I am right here. So what are the links I should use? My outgoing interface list. What should I use in order to send this traffic? I will send it on the link that connects me to switch 101. So instead of flooding, I'm only going to send it to switch 101. This is going to be my outgoing interface, like the multicast oil, right? It's exactly the same thing. I send on this interface. Now when switch 101 receives, it does not even look into the original Ethernet. It does not even look into it. It looks into the destination, the outer header, 12Fs. Oh, so it's a broadcast. So I will look into the F tag. What is the F tag I am supposed to use? I will see that. And F tag is 1, which is set by switch 1, right? So it will look, okay, I am supposed to use this tree. According to this tree, this is the only outgoing interface, according to this tree. So what I do, I will only send it on this link. Oh, the link is not even there. Okay, yeah. I will send it on this link, only on this link to S2. Same thing. When S2 receives it, couple of things are going to happen with S2. Number one, because it also has classical Ethernet ports, we call them as edge ports or classical Ethernet ports. Remember I told you the VLAN information will be added here. So it will send it to all the ports in that VLAN, in the classical Ethernet. So let us say there are these 2 ports. So I will decapsulate the packet and I will send it on these 2 ports. That is my classical Ethernet. Because I also have edge ports, I will send the regular Ethernet on this. I don't know, right? I don't know where 10.6 is. Maybe this is 10.7, 10.8. I really don't know where 10.6 is. So I will send it. Along with that, because I am supposed to use F tag 1 given by the source switch, according to that F tag, I should send it on 102 and 103. Except the incoming interface, I will send it to all the other outgoing interfaces. So in the fabric, I will send it to 102 and 103. Okay. Oh, wow. I did a small mistake here, guys. You must have observed it. I did not. It is going from switch 101, right? It's come to 101. From 101, it goes to switch 2. I made a mistake. So it is going in this direction. So switch 2 received it and switch 2 sent it to those classical Ethernet ports falling under that VLAN. And also, there is extension to the tree here. So I will also have to send it to switch 102 and 103. So I will send it to 102 and 103. So now when 102 receives it, it does not have any classical Ethernet. And remember, I can also have classical Ethernet, okay? I'm just not drawing it here, but I can also have. So in this example, it does not have any classical Ethernet. However, it looks at the destination 12Fs, and then it looks at the F tag. I'm supposed to use this F tag. And according to this F tag, switch 102 is in the tail end, like it's in the edge of it. Because I received it from switch 2 and I don't have any other classical Ethernet ports, I won't send it to anybody else. That's it. So S102 is going to take it and simply discard the frame because there is no classical Ethernet and there is no other branches to the tree. So I discard it. I don't send it to anybody else. When 103 receives it, same thing. I look into the destination 12F. Because of that, I look into the F tag, and F tag is 1. So according to this tree, I have 3 branches. I received it on S2. I will send it on S3 and S4. So when S102 received it, it is the one it is going to send to S3 and S4. And when they receive it, they check. Okay, I have to use F tag 1. And according to the tree, I don't have anybody else, no other branches. So I don't send it back to the fabric. However, I have my classical Ethernet ports, right? So when the VLAN information is tagged here, I use that and send it to those ports in that VLAN. Encapsulate the frame and send the original frame there. Now I want you to observe. See, in the original, in the frame that I received, in the frame that switch 4 has received, as a matter of fact, switch 4 received it, 3 received it, and 2 received it. Like all of them received it, right? Okay. When they received it, they received the source of the frame, which is switch 1. In the original packet, in the original Ethernet frame, they also have the source MAC, destination MAC in the original frame. Source MAC is 5A, right? If you closely observe, right, by looking at this information that is come to switch 3, switch 4, and switch 2, can they do a mapping? Can they do a mapping? Oh, okay. Switch ID 1 is where 5A is connected. Can I do that mapping? Or even better way of saying is 5A is connected to switch ID 1. Can I do this mapping? Do I have that information by looking into the packet? Yes or no? Because in the original Ethernet, source is 5A. Who is sending it in the outer header? Switch 1. So with that information itself, I can know 5A is connected to switch 1. I can know that, right? Yes or no, please?
Yes, we can.
Yes. However, switch 4 will not learn it. Okay. Switch 4 will not learn it. Switch 3 will not learn it. Switch 2 will not learn it. Nobody will learn that. Even though I can learn, I won't learn. I'll tell you why. So now what happens? The frame will be sent to all the other systems. 10.6 received the ARP request, the original request, because the IP is matching there. And now it is responding. Now when 10.6 is responding, it's a unicast message. Okay? It's a unicast message. So when the frame comes to switch 4, answer the question. Does switch 4 know where 10.5 is? 5A, where it is? Does it know? Guys?
But as soon as the original frame came into S4, during the time it would have recorded.
But I just told you, it won't do that.
Yeah.
So, does it know? No.
No.
So, this is a critical point to observe. Even though I can learn it, the switch 4 did not learn it. Now, because switch 4 did not learn it, when the packet is coming here, first things first, I will learn the source MAC address 6A and the port number 1/3. Because it's classical Ethernet, I will learn it. So nothing changes. But I don't know where 5A is. I must have recorded, but I did not. So now what happens? This becomes an unknown unicast. The frame you got is a broadcast, but the frame you are returning in the fabric, that is an unknown unicast. The switch 4 does not know where it is. So now what? Now it becomes easy. Just like the broadcast, unknown unicast also will use the multi-destination tree. So switch 1, in this case switch 4, it can pick the same F tag, it can also pick a different F tag, doesn't matter. It can use any of those multi-destination trees. Just as a side note, at least as of now, even though there are 2 F tags, for some reason fabric path uses only first F tag. Okay. We say in theory that it uses one of the other, but at least at this point, it is using only one of them. So the second one is kind of behaving like a backup, that's it. Okay. But anyways, the point is this. It will use the same F tag and again send it on that F tag. But this time one small thing, the destination address in the unknown unicast is a reserved MAC address. There is one 48-bit MAC address that is reserved MAC. They call it as MC1. In fabric path, they call this reserved MAC address as MC1. So there's a value to that. Okay. So this is used for unknown unicast. But that address is not really significant. Once I know that this is used, I will look into the F tag, and that is significant to know which outgoing interface list to use. Now, just like before, if I am using the same F tag 1, I am switch 4. So according to me, I will send it to 103. So the frame goes to 103. And now I don't have to explain that much. 103, it will send it to S3 and S2. It will send it to S3 and S2. S2 is fine. This is an unknown unicast, right? So it will, if there are any classical Ethernet ports, I would send it to those respective ports because I don't know where it is. I simply flood it on my classical Ethernet. Same thing happens with switch 2. However, there's an extension to the tree, right? Because F tag is used. Switch 3 doesn't have any branches, so it will simply send it to only those classical Ethernets after decapsulating. When S2 receives it, it will send it to 102 and 101. So S2 will send it to 102 and 101. And when 102 receives it, it has no other branches, so it will just stop the propagation. Again, if it has any classical Ethernet, it would have sent it there, but at this point, it's not there. When switch 1 receives, it will send it to, switch 101 receives, it will send it to 1. So inevitably, the frame comes here. When the frame comes to switch 1, see, the original Ethernet frame is now return packet. Return packet, the inside, the original is source is 6A, destination is 5A, right? It's a unicast. Outer source is switch 4, destination is that reserved unknown unicast, right? NC1 we call it. That unknown unicast reserved MAC address. By just looking at this, can I realize, okay, 6A is connected to S4. Do I know that by looking at the frame? Yes or no? Answer please, important.
Yes.
Yes. Will I record it? And the answer is yes, I will record it. Okay. What do you mean? S4 must have done the same thing, right? When the packet has come in the forward direction, it must have done the same thing, but it did not do, I said. But now I am saying S1 will record it. Why did it record? What is this logic? This is called conversational learning. What I have just explained you, shown you, is conversational learning. What it means is, I will learn the MAC address of the source and the corresponding switch only if I know the destination in my MAC address table. If I have the destination in the MAC address table, then I will learn about that source. Otherwise, I will not learn. The reason why they did this is in order to save the memory of learning all the MAC addresses. See, anytime something comes, unknown or broadcast comes, it will be sent in the entire fabric, right? Loop-free multi-destination trees are used and sent to the entire fabric. Now, if I start learning all the MAC addresses, that's very easily going to consume a lot of memory. And remember, I'm using this in a data center, like thousands, I don't know, lakhs even, hundreds of thousands at least. So that's a lot of MAC entries. So they said, okay, if you know the destination, when will you know the destination? When they are coming from the classical Ethernet. So in other words, they are saying, if you have any systems in the local LAN to which the sources are communicating, then make an entry, otherwise no. That's what they are saying in English. So now I have learned the MAC address and the corresponding switch ID again for the first time in the MAC address table, like literally show MAC address table. That's the same command we give. In the MAC address table, we see a MAC mapped to a switch ID, not the port number, but a switch ID. Now at this point, I know where 5A is, so I decapsulate the packet, fabric path frame, and I send it directly to this port. Now, the second frame is coming. Now when the second frame comes, I learn the MAC address, I refresh the entry, my classical Ethernet, right? I refresh the entry and I will look for the destination. Do I know where the destination is? Yes, I know where the destination is. So now I have answered both the questions. How is bump traffic handled? And how will I know the MAC to switch mapping? Now you got it. So now I know where it is. I am going to send it in a unicast fashion. My original source is going to be 5A, destination is going to be 6A, and my outer frame, is going to be switch 1 ID and switch 4 ID. Now I look into my routing table. I have two paths. Now I will send using ECMP. one flow, I will send it in this direction. When the switch 101 receives, the destination is switch ID 4. It looks into its routing table. 35 is the optimum path. I will send it in this direction. Tomorrow, if this link goes down, I have alternate paths of going. I'm just doing my routing, nothing else. I don't even look into the content, the original source, who is it, the original destination, I don't even care. I will simply route it to this guy. Once this guy receives it, destination is switch 4, so it will open it and look into it. And now I will make an entry of 5A and the port, and the switch ID of 1. Why will I make the entry now? Because now I know the destination. Previously I did not know, but now I know the destination. I will make an entry of it, of the source. Conversational learning. And by that time I know where 6A is, I will directly send it this.
But what is the difference here? Previously also similar to that. Previously I was inquiring about 6A. Now I am not inquiring.
I am inquiring. You mean to say, why did I make the entry now, not before? Correct?
Yeah.
Yeah. Before also I was inquiring. When I inquired my MAC address table, 6A entry is not there.
Okay. Switch 4 itself, I don't know what there is 6A. Switch 4 itself doesn't know who is 6A.
When the first time frame comes, switch 4 did not know, no?
Correct, got it.
Only when the response came, 6A entry was made here. Then I start learning. So once the second frame comes to switch 4, now both of them know the locations and the mapping of the switch. So now when the frame comes from 10.6 to 10.5, you are routing the frame, purely the fabric. They don't even care the original source, original destinations. They just route based on the switch ID, using the routing table. They do ECMP. Tomorrow, you want more bandwidth, you simply add another link. I'm just doing another ECMP. Another link. I do another ECMP. That's it. Nothing changes here. You have exponentially increasing. No SDP, no blocked port, no VPC, no arbitrary, no fixed connections. Randomly. Tomorrow I wanted to add another for port density. Yeah, add another fabric path and add another switch. Connect it to another one. Just configure fabric path. Just like that, you can expand. Literally. You don't have to do anything here. It just happens automatically. Okay. All right. So now with that said, few points I wanted to highlight. So this is it. Okay. But there are a few points which I want to highlight from a deployment perspective. One, by default, the VLANs which you have created, for example, in this case, VLAN 10, they will not be encapsulated on the fabric path. They will not be sent on the fabric path. So whatever I talked about is not going to happen. Yeah, by default, it won't happen. If you wanted to allow those VLANs traffic to be using the fabric path links, you have to do that second config I said, right? There are two configs which you should do. One is enable fabric path on this. And the second thing you have to do is you have to configure the VLAN mode as fabric path. You have to do that. And that's it. That's the second command you have to give. So all the VLANs that you want to allow on this fabric path to communicate, all of them you will configure the mode fabric path. So you go to the VLAN 10, enter, and mode fabric path. That's what you do. So that is the other piece you should be doing. Okay. So keep that one point. Second point, this is not supported by, how should I say? In your Nexus, there is this F cards, which are used typically for layer 2 connections, and M cards, which are layer 3 capable. So at least as of now. Tomorrow, I don't know if it changes or not, but it's not changing for a while. But at least for now, fabric path, in order for it to run, you must have F cards. You cannot connect it on M cards. Like layer 3 cards, you cannot connect. It must be an F card through which you should connect. So those ports that you're connecting to the fabric path, you should configure that to be, those ports should be physically F cards, not M cards. So again, look into the product spec and see whether the compatibility is there or not. So that's another thing I want to highlight. Third thing I want to highlight is, okay, you have your fabric path and all that glory running and everything is fine. Okay. So now I'm not drawing the whole diagram, but what I am drawing here is the fabric path cloud. So fabric path, you are all connecting to the fabric path. So this is the fabric which I have just circled. That's it. Okay. Now what you are trying to do is you are trying to switch 1 and switch 2. You are trying to configure VPC on this side. You are trying to configure VPC on this side. So there is this server 1, I don't care, it is a server 1 or maybe a switch 1, I don't really care. But the point is, this is VPC, meaning this is for the downstream devices. It looks like a single switch, right? It looks like a single switch. All right, that's fine, no problem. Now, if this is 10.5, trying to communicate to maybe 10.6, for the 10.5, it's a regular port channel here. So the data will be sent on this link or on this link, right? For example, the data is sent on this link. If the data is sent on S2 side, again, S2, it is going to, for example, it has an ID of, S1 has an ID of 11, and S2 has an ID of 12, switch ID. If it uses, okay, if it uses switch ID 12, my source is 12, destination is 14, okay. So 14, the packet will go from here routed to 14, no problem with that. Return packet will come to what? Return packet will come to S12, switch ID 12. And the data will come here. Okay. What's the problem? The problem is, if the data is coming in this link, then I am not using redundancy. I am not using load balancing, right? Some data should be coming to S2, some data should be going to S1, so that load balancing will properly happen. But that is not happening because I'm using my ID. Second, tomorrow if this link goes down, right? Tomorrow this link goes down, then the data will be sent on this switch. Now what happens? The mapping will change. Initially, 5A is connected to 12. Now it is connected to 11. Right? Guys, able to hear me? Okay. So now it is 11. So there is a reconvergence event happening. Now in reality, the two switches are looked like or felt like a single switch. No? For the downstream devices, it looks like a single switch. The same thing should happen with the fabric path also. In the fabric path also, they should think the switch 3, switch 4, switch 5, whatever, they should all think of this as a single switch. They should think of this as a single switch. So when you are running VPC downwards and when you are running fabric path upwards, couple of configurations is what you do. Number one, very, very important. sometimes people don't do it and they will face problems. This port channel, the peer link, this must be configured as fabric path. Not only this port, even these peer links should be used, should be configured in the fabric path mode. Why? Remember, data traffic will still be going on this link. So if you don't configure it, some of the data patterns will not work. So you must configure peer link on the, you must configure fabric path on the peer link. This is number one config you have to do. The second config you have to do is you go to the VPC and you create a switch ID. We call it as the VPC switch ID. And I will create something like 112. So when I do that, this is exactly what happens. When the frames are coming from the VPC member port, my ID will not be 12. I won't use my local ID. I will use 112. When I form adjacencies, I will now have in the ISIS, I will now have 112 as another ID. Who has it? Both these switches have it. Both are sharing this common ID. So tomorrow when their route has to come, first of all, the mapping here is going to be 5A is connected to 112. Instead of 11 or 12, it will be mapped to 112 because that's going to be the source switch ID when I send the data in the fabric path. So that is how your mapping is going to be. So when the return packets are coming, because 112 is reachable on both the sides, because both of them are 112, if the data is coming to this, maybe switch 101, for example, and they are connected to 1 and 2, now I will start doing load balance. Some packets I will send it to this switch, some packets I will send it to this switch. So now I will have proper load balancing happening. Second, tomorrow something goes wrong with this switch. There is no reconvergence event in the mapping. Sure, my ISIS table will reconverge, but from a data plane perspective, they have no reconvergence event. It just still goes to the fabric path, and from there it goes to the 112. This time only one path will be there because the second is down. So these are the two things you should be doing. One, peer link should be activated with fabric path. Two, you will go to the VPC domain and configure the switch ID. And when you do this, you have just configured VPC Plus. That is what VPC Plus is, nothing else. VPC to the southbound or fabric path to the northbound. Are we clear with it? Yep.
Yeah, Kalyan.
All right. So, pretty cool. One and only one, maybe major drawback is Cisco proprietary. It is so stupid proprietary, I'm sorry to use that word, it does not even support in all the Nexus boxes. It is so stupid that it does not support in all same box different line cards. You have to have a specific type of devices which support fabric path, and you should also have specific type of line cards that support fabric path. Okay, so marketing guy will come and say, we have a beautiful, fantastic technology. Only thing is you have to give me $350 million or $3 million to get the technology. Nothing. You just remove those 20 switches which you have and take these new 20 switches. But I already have Nexus. No. That card will not work. So you at least take these 20 cards. Okay, fine. Thank you very much. We will get back to you very soon. Okay. So I heard a few people, deploying Fabric Path, and I asked them what happened. They said nothing. Like nothing. We don't even remember that we configured Fabric Path. It's one time we did it, and everything is just working. They did not even get back to it. No problems whatsoever. Really, no problems. So technology-wise, it's a very good technology, but there's a lockdown, like proprietary lock. That's the problem you have with Fabric Path. And today, at this point in time, we have definitely a better solution. We definitely have a better solution, and therefore, eventually, if not today, tomorrow and day after, eventually Fabric Path will go away. It will just go away. Okay. But we have it, we have to know. Some networks still use it. So that's it. All right. Any other questions regarding the Fabric Path? I have one last point to highlight here. One last point. With regards to Fabric Path, you can basically have 4 gateways. I can configure up to 4 HSRP gateways. Parallelly, I can have HSRP running on this. Okay, so instead of VPC, where you have 2 active gateways, you can have 4 parallel gateways with Fabric Path. This is the first point. And the second point, which is very, very, very important, I must tell you that. Once you enable Fabric Path, these ports, which are called as edge ports, they are automatically enabled with root guard. Root guard is enabled on all these ports. So what does that mean? What does that mean for us? If you have a Fabric Path setup like this, if you have your Fabric Path setup, and you also have your traditional switched network, right? You have your other switches going on here, connecting here, another set of switches. You have your own LAN. Maybe some part of it you made it Fabric Path. You cannot have a root switch anywhere here. In other words, once you deploy Fabric Path, that one Fabric Path domain is going to act like a single switch. It's just going to act like a single switch. And that must be the root switch. Because the root guard is there, if you give a better priority on this side, they will be blocked. You can't even disable that, so be careful. You just can't disable that. It's going to be root guard, and superior PPDU comes, you will immediately block it. Okay. And in all fairness, in proper designs, that's fine. That is what you want anyways. Okay. But just a point to remember. Okay. And by the way, how will they all look like a single switch? All of them will use a reserved MAC address in the BPDs. So for all of them, they will use the same bridge ID and send it. So you connect it here, you connect it here, you connect it here. As far as the switch is concerned, the switch will see all of that as a single switch. Okay. So keep that in mind. Okay. Right. That is it. Yeah. So that's where I would like to draw the line for Fabric Path. We will take the break. We will come back. And once we come back, we will talk about OTV. Okay. So
Yeah, we can see now.
Okay. Okay, so what is the purpose of OTV, Overlay Transport Virtualization? That's the full form of it, but what is the purpose of it? Now, what we discussed before is Fabric Path, which is a data center technology, which is inside the LAN. Basically, the idea is to avoid the STP hassles. Anything that is related to STP, we just wanted to avoid. We just wanted to completely eliminate it if possible. So that is the basic idea of having Fabric Path. But then OTV is completely a different solution altogether. And it is used for primarily, and the only reason actually, is DCI. What is DCI? Data Center Interconnect. Now, what is the special name? Why do I call it DCI? Just a WAN, right? Yeah, it is just a WAN. But the moment you say that I have some systems of 10.x here, which are connected to another branch office where I have another 10.x systems. And if you wanted these two systems to talk to each other, now you have 10.5 here and then 10.5 or 10.6 here. If you want this to communicate to each other, this is where I take a WAN connection, which we now call DCI. Basically, in other words, what I am trying to achieve with this terminology, DCI, is basically layer 2 extension. This is what I wanted to achieve. So if this is the case, this is where we call the connections you take as DCIs. Okay. The layer 2 extension is what you wanted to do. Now, there are a plethora of questions which people may keep asking. What if I have to communicate from outside? So maybe this is data center. And if you want to communicate from outside to 10.5. So maybe there is a internet connection somebody took, or maybe a private company, private branch office, which is connected to the WAN. I don't know how. It could be through MPLS, it could be through internet, doesn't matter. Now, if they want to communicate to 10.5, how will they go? Because as far as my routing is concerned, in my mind, 10.5 is not the point. 10.0 is the point, right? I only find the destination network. And so if I have two routes to reach the destination network, which way will I go? How will the packets reach the correct branch, correct data center? Okay. And no, I can simply give you the answer. Okay, for this router, this is closest because 10.0, according to their internal metric, this is closest. Okay, if the packet goes here, then 10.5 is not here. So then how will the packet be sent to this guy? Okay. I am not going to answer those questions. All right. For now, understand this much. If, for example, the packet still goes to this side, because this is a DCI interconnect, like the L2 extension which I took, this will be flooded. This will be flooded in the LAN, right? If 10.5 is not known, I will flood it in the LAN. This router, being the edge device, is going to send any layer 2 frames to all the devices here. So which means whenever a frame comes from any of these places, whether it is a frame coming from the WAN, whether it is a frame coming from this side, the same question raises, right? When 10.6 wants to communicate to 10.5, the same question comes. How will the how will this router know 10.5 is here? Maybe there's another branch which I can also connect. There's another branch which is also having 10.x, my company, second, third branch. So the same question will come. Okay. So from a routing perspective, from a third person, third company trying to access this, it will come to one or the other places. And once it comes there, how is it going to identify? How is the edge device going to identify where the location of the system is? That is a common function, right? Whether the packets are coming from 10.6 or whether the packets are coming from the other, some other WAN and coming here. Okay. So I will answer this question. I will answer the question, okay, when 10.5 wants to communicate to 10.6 or 10.6 wants to communicate to 10.5, how exactly will that communication happen? We are going to talk about it. Okay, we are going to answer that question. All right. I will introduce this. We are not going to discuss it. If the connections, if the requests are coming from somewhere else, is there any method or technology that I can use in the DCI so that I can exactly go to the right place instead of going to this and this guy figuring it out and sending it to this side, which is unnecessary bandwidth consumption on the link here? Is there any technology in the WAN or the DCI where as soon as the packets come to 10.5, the routers somehow know that it is on this side of the network? Tomorrow, if this 10.5 moves from here to the other side, is there any technology here that will allow me to know that the packet, the 10.5 is on this side, and so I have to route the packet here? Is there any technology here that can help me optimize my routing? And yes, there is a technology, and that is what Lisp is all about. Okay. And this I'm not going to discuss. Okay. We are not going to bother about this. What is this? How will it work? We don't care. Okay. However, your communication is still completed. It may not be optimum if it is coming from outside, may not be optimum, but inevitably reachability will be there. Okay. So let me draw the diagram again. So we have our router, not a router, the edge device, which is connected to your traditional LAN network. I don't care what technology we are using here. Okay, so just a traditional LAN network, and you have 10.5 here. Now you are connecting to the DCI, and from there you are connecting it to another branch of yours, which is another edge router or edge device, we call it. And from there again, you have your local LAN. On a VLAN by VLAN basis, remember in the LAN, you will have different VLANs, right? On a VLAN by VLAN basis, you can extend this networks. You always have to assume maybe there will be another branch also. You may have to assume that. So, which is also having the same network. So basically what you are doing is you are expanding your LAN, just the LAN, but you are expanding geographically into different places. Locations, different locations. Generally, why we do that? Generally, it is data center and data center recovery sites, DR sites. Okay. So generally for that, you will have this kind of a setup. So you may want to expand your network. So something goes wrong completely here, your VMs, your network, there is a second server sitting here and it will start taking the request coming from the public or private, doesn't matter. All right. So now the question, okay, how will this happen? How can I do this? Well, there are different technologies, okay? The technologies that we had, one of the oldest ones is the dark fiber. The logic of dark fiber is very simple. You literally have your edge device is a switch. You connect your gigabit Ethernet or whatever Ethernet you have to the service provider switch. And through their chain of metro Ethernet connections, you are going to get connected maybe from another switch in the service provider to the guys, are you able to listen to me? I just got this network connection problem.
Yeah, Kalyan.
Okay, good.
Yes, Kalyan.
All right. So this is going to get connected to the other branch of yours, which is again a regular switch, no big deal. And then you have your Ethernet port. And from here you connect. Now, almost like literally, it's just a switched network, nothing fancy. Just your switched network. There is some technology which they will use. Typically, there are multiple technologies, but one of them they typically use is Q in Q, we call it, which is basically multiple customers will be coming here, right? So when multiple customers are coming, it may be one customer on this side, another customer from somewhere else. They may be connected to this. So to identify the customer, they will give a VLAN for the customer. And then you have your own VLAN, right? Which you are going to expand. So what you will see is two VLAN IDs. One is the internal VLAN, which is VLAN 10, for example, and then the customer VLAN will be there. So when the internal switching is happening, it all happens with the outer VLAN header. And once it reaches the customer edge, the outer VLAN is removed and the inner VLAN will be there so that internal switches will know how to send it to that particular VLAN. So a technology like this, Q in Q, you kind of use that. But end of the day, it just switches. Yeah, geographically separated, it just switches. So this was one of the technologies which people used. The only limitation with this technology, I mean, a couple of them are there, but one of the limitations is the distance. Like not every provider can provide geographically this metro Ethernet. Short distances within city, maybe if it's a big provider, maybe to an extent they can provide. There is a geographical limitation on how far you can go with this technology. Okay, and if I say that these are used for disaster recovery sites, generally you don't put it in the same geographical location, right? So generally at least a city away they will put, so that if something goes natural or political or economical, whatever disaster happens in that complete city, you can hopefully have the other city calm and quiet. So yeah, you can use it. People did use them. People even today, some of them use it. But the geographical limitation. Okay. There is another technology which you can also use, which is what we call MPLS. So it is what we call L2 VPN. With this, what you have in the backbone is the MPLS setup. Okay. The same setup like what we had, you can have the same. But this time what you do is you have your router connected to your LAN interface. I mean, connected from your LAN interface to this router. And then the customer edge is connected to the other side. What you do is you create in VPLS terminology. What you do is you create a pseudo wire. So basically what you do is, the configuration is also very simple. What you do is any traffic that comes here, send it to this side. That's it. It's almost very similar to a GRE tunnel. It's as simple as that. You create a pseudo wire, you tell what the destination route ID is, and you say the encapsulation is MPLS. So there will be like L3 VPN labels, right? You will have an L2 VPN label, and all the data will be sent on this wire. So you will map this physical port connecting to the customer side to the pseudo wire, which is the logical interface, and you do the same thing here also. Very simple, straightforward thing. So this allows me to have geographically distinct places. As long as the service provider is providing MPLS backbone, we can get this connection. Okay. And it is very safe to say today, like every provider has MPLS backbone. Very safe to say that. So in a drawbacks of VPLS, you can tell, in theory you can tell MPLS should be there in the backbone, which is true. Without MPLS, the VPLS won't work. But it's not practically a problem because pretty safe. All the providers have MPLS backbones today. Okay. Now, whether it is dark fiber as a solution, whether it is solution like VPLS, there is one common problem with both of them. The common problem is, how do I put it? There is no control plane isolation. There is no control plane isolation. What do you mean by that? See, literally, even though they are geographically separated, literally this is like switch 1 connected to switch 2 directly. That is what it is. They can, when you say show CDP neighbor, they can actually see each other. All your STP, BPDUs, everything will be sent. Your data, unknown, unicast, just like a regular flooding. If I want to communicate from 10.5 to 10.6, sitting somewhere here, I'm going to flood it to all the ports except the port through which I receive. So I receive it on the switch 1. Switch 1 does not know where it is. So it will send it to all the ports except the port through which it receives. When it comes here, it doesn't care what you are sending. Is it an R broadcast? Is it a STP BPDU? Is it a HSRP hello packets? I don't care. Whatever you send here, I'm just going to send it on the link to the other side. My job is to just send the data. So the data will come here. This switch does not know where it is, so it is going to be sending to everybody. BPDU is coming. So now, if this happens to be the root switch, this will be the root port. Like, physically it is separate, but logically it's like 2 switches connected, that's all. So if this is the root switch, now everybody in this is trying to find the best path to go there, because STP, they have to find the best path to go to the root switch. Right? And R flooding, any other flooding you do, everything, whether it is Metro Ethernet like this or whether it is a setup like this VPLS, it's just one control plane. Now, for starters, like initially, it was good, right? Because that's the whole purpose. That's why you wanted it. L2 extension you wanted, right? No, so you got it. But that's design-wise, traffic pattern-wise, unnecessary bandwidth consumption-wise, it's having problems. The control plane is having problems. And that is where they came up with the solution of OTV. OTV was developed primarily for the purpose of this L2 extension. So they have done a lot of optimization. So what is that? How will the data traffic go? How will they know each other? Pretty much the same questions we had before with Fabric Path. Pretty much the same I will have to answer in this setup also. Okay, so before I answer, looks like Deepak gave some messages. There's no CE in this case. Is there any CE? Yeah, I mean, arguably, this is the CE. Customer edge, right? Is it a router? No, it's a switch. If you're asking, do I have a switch or a router? And yeah, it's a switch. You don't have a router there.
Okay, actually, I was talking in the VPLS.
Yeah, in the VPLS only, I'm saying. You're on.
Okay. Okay, so switch is as a CE.
Yeah, switch is the CE.
Okay, so the same means subnet we are extending means like there is a 10.5. Okay, yeah, got it.
All right. Okay. So, okay, how is this going to work? What is all this? Okay, here is the thing. First of all, this interface, let us get some terminology correct. This interface, this is called as join interface. This is the physical interface through which you are getting connected to the DCI. In other words, you are just joining the layer 2 extension. And this is the internal interface. And then what you do is you are going to create what is called the overlay interface. So this is the logical interface which you are going to create on each of the routers. And what happens is when the data is coming, which is an Ethernet frame, this is going to be encapsulated. Logically, it goes to the overlay, encapsulated into the overlay frame. We will see what that frame is. And then it is sent on the join interface. And pretty much the entire configuration will be done on this overlay interface. So now you have a logical tunnel that you're going to create between them. Okay. So that's the basic idea. Okay. Now, what encapsulation will be there here? Super surprising and very interesting. This is where the future is. 5.5, 9, whatever, and then 10.8. Yes, please.
For this suppose this DCI.
Your voice is breaking completely.
Now, are you able to hear me?
Yes, perfectly.
Yeah. So site A, left side, site B, right side, right? So if the DCI is one provider and site B is a different provider, how
I don't care. Okay. As a matter of fact, one of the very, very, very big advantages of OTV is this could be internet. I don't care.
Okay, as long as connectivity is there between the edge devices, no issue.
No issues. Okay. All right. And again, why no issues? You will understand once you know how the working is happening, how the packet flows happen and how the discoveries happen and all that. Okay, so for now, just starters. So you have this site A, site B, and site C, whatever, and then you have your edge devices, you have a join interface. So the first thing I want to understand is the encapsulation. And that's a very, very, very cool thing. 10.5, same thing. See, from here on for the future of networking, guys, especially that switching and all that, never forget this. I mean, if you forget this, your career is closed. Okay, I gave a very strong statement, but it's important. Okay, routing the frame. Never forget that. That's what you're going to do. That's what we already started doing, and that's the future of everything that we are going to do. Okay, so again, you have your original Ethernet frame, 10.5, which is the 5A, 10.6, which is the 6A, and the internally packet is there, which has got 10.5, 10.6, I don't care. This is the Ethernet frame. What you do is you are now going to encapsulate this into a IP packet. The source IP address is going to be 5.1. The destination IP address is going to be 7.9 and the packet is sent to the PCI, whatever that is, MPLS, WAN, PCI, Internet, I don't care. So like your fabric path, which had a special encapsulation, special switch IDs, special F tags, there is nothing like that with OTV. It's just encapsulation into an IP packet. So once the packet reaches this router here, it just has to do the routing based on the destination IP address. That's it. What is inside that is actually Ethernet frame. I don't care. I just have to route the packet with the destination IP address on the outer header. So the packet comes to this router, 7.9 knows about this, and then it says, okay, this is for me, take out the packet, look into the frame, 6A, I know it is on this port, I will just send it on this port. This is the overall flow. This is how it has to be. Again, just like with the fabric path, I have a lot of questions to answer. Okay, how will they know? First of all, edge devices, maybe switch 1, switch 2, switch 3. How will they know each other? Question number 1. Question number 2, how will they know where is what? So if 10.7 is here, for example, how do I know? How does switch 1 know? If I want to communicate to 10.6, I have to send it to 7.9. If I have to communicate to 10.7, I have to communicate to 10.8. How will it know? I don't have to answer the third question. What is the identification for the switch? We already know that. It's the IP address of the join interface. That's it. So ID is no problem. 5.1, just the IP addresses is what they are going to use. But the other questions I still have to answer. When 10.5 wants to communicate for the very first time to 10.6, it is going to send an ARP broadcast request. And when it sends an ARP broadcast request, how will it be handled? So again, the same question. How will the bump traffic be handled? Broadcast, unknown unicast, and multicast traffic. How will all of that be handled? Okay. Here is the answer. First of all, in order for these edge devices to know each other, as soon as you enable OTV on this, guess ISIS is activated again. It's so funny. Once upon a time, we used to study in CCNP ISIS. Then after some time, almost for 10 years, 12 years, they have removed it. Not 10, 12 years, more than that. They removed ISIS. No, nobody is using, nobody needs it, so we'll remove it. And last year, Feb 24th, everything changed, right? Certification pattern, they changed the syllabus, lot of it has changed. ISIS is added. Now they want ISIS again. It's not like people will use ISIS in the production environments, like in the ISP as an IGP protocol, but now they want us to know, yes, this protocol is not going anywhere. This is staying. This will continue to stay. Only because of that important features too. Without an IP also it will work. TLVs. Because of these two important features. This is not going anywhere. Okay. All right. So ISIS is going to run on the edge devices. Okay. Now I can simply say, or maybe you have already assumed, okay, ISIS is there, so neighbor adjacency will be formed, and so they will know each other and they will know how to reach each other. You might have thought like that, right? There's a problem. ISIS is going to run, Okay, that is not a problem. If I look at my fabric setup, which I had before, when I say ISIS is running, yeah, it is running on all these switches. It is going to run on all these switches. ISIS is going to run on all these switches. They are all directly connected to each other. Neighbor adjacencies will be formed, hello packets will be sent, which will be received by the switch. All of that is going to work without any problem. They are all connected to each other. And by the way, ISIS also sends multicast, right? Hello packets and all that. But whereas here, okay, I'm running ISIS, you will send it, ISIS hello packet. Will the DCI support it? Will your DCI send it to the corresponding edge devices? This is not an MPLS L3 VPN which you have taken. Remember, this could be anything, including internet, I said. Even if you say it is MPLS, you have 20 branches. Okay? You are sending your ISIS updates, ISIS hello packet, first of all. When you send it to ISIS hello packet, how will this guy know that these two are in the DCI interconnect, there is a layer 2 extension there? How will they know? In other words, when the hello packets are coming from ISIS, how will the provider send the hello packets to these two routers or to these two edge devices? Similarly, when the edge devices are sending, they should be sent to the corresponding other edge devices. In other words, how are the hello packets exchanged between the edge devices? If they are exchanged correctly, then yes, a neighbor adjacency will be formed, they will know each other, all that is good. But how will they form adjacency? How will my hello packets go? It could be anything in the WAN. So yes, in the first look, it looks like it is also like fabric path, ISIS will run and it will form. No. It's different. Logic is the same, but doesn't work in this setup. So here are two options for you. One option is, when you configure your OTV, you will configure what is called as, first of all, let me take one step back. The two options you have. The first option is with multicast support. Your service provider should support multicasting for you. They should say, okay, we are agreeing your multicast. We will take your multicast up. Some providers may support, some providers may not support. So, without multicast support from the DCI, for example, as I think Madhu was asking, if it is a single service provider, I won't say they will support it then also, but I will say at least they can kind of, depending on their business logic, whatever, they may accept it most of the time. Maybe. I don't want to give any percentage, but they may accept because it's all one service provider. If you are going with multiple service providers, chances are less. Remember, multicasting between multiple service providers will also work. It is also there, and a lot of public multicast applications, they will use that. Okay, it's not like it is not there. It's not like if I have two different service providers, my multicast traffic won't go. It will go. No problems with that. Okay, but the chances will come down. Okay. Again, in both the cases, whether it is a single service provider or multiple service providers, no guarantee. Okay, but chances will come down if you have multiple players in the picture, because they all have to agree to this multicast. You have to buy that from everybody. They may have their own multicast ranges going on, and some providers like Tier 2 may not even support that multicasting. Okay. And the third is like internet. If you go for internet, no guarantee. I mean, definitely you will not get multicast. I mean, nobody wants to go with internet when you take a layer 2 extension, but you can do it. You can. Okay. And that too, today, quality of internet is also good, right? So maybe they may do it. So the point I am boiling down to is this. Your provider, if supports multicast, the way ISIS adjacencies are formed, updates are sent, will be in one style. If the multicast is not supported, then there is another alternate way you will have to do things. Again, end goal for any of this, what I'm discussing, is they should know each other, right? These guys in the DCI edge devices, they should know about each other. And ISIS is the process, but ISIS should be sent back and forth. Okay, now with that said, first let me tell you what happens if multicast is supported. If multicast is supported, we will configure. So the service provider will say, okay, fine, I'm giving you a multicast address of 232.1.5.5. This is the multicast address to which you have to join. This is the multicast address to which you have to join. That's what we will say. Okay. So now what happens, according to the provider, you are this, you in the sense this particular port, you are simply a host. You may think of yourself as a data center, but for the service provider, you are simply a host. So what you do is you run IGMP on this. You send, once you run IGMP, you send join messages, right? You know all the stuff. So what happens is they have given you a control plane, and for that, for example, this one. So this is what we call control plane address. So they'll give a control plane multicast address if they are supporting multicast. So what you do is you will join the multicast group. So there is a rendezvous point through which you will be going, and that stuff it's none of our business. They will take care of it. Whether they are going in a dense mode, they are going in a sparse mode, if they are going in a sparse mode, taking that join message to the rendezvous point related configuration, they will take care of it. None of our business. But what eventually happens is, now all this setup, the multicast routing, will have outgoing interfaces taking me to those respective branches. Why? Because each of them is sending a join message. So now the entire TCE environment, they know, okay, this is customer whatever is given this multicast stream. Whenever ISIS sends its packets, it could be hello packet, it could be update packet. Whenever it sends this control packet, ISIS specifically, it will send it with the destination of that multicast. These are control plane information. So once the multicast packets come, they, according to the multicast routing, they will be sent to the respective edge devices. Similarly, the hello packets come from the other side. They will be sent to the group using multicast routing, and they will all start receiving the hello packets. They will start looking at each other as neighbors. And then they will start sending their updates. What updates they will send is a very important point. I still did not talk about it. Okay, but they will now, at least you know now, that they will start knowing each other. They will be able to send updates to each other. And you know how it happens. Okay. So this is one method. But what if multicast is not supported? If multicast is not supported by the service provider, in that case, what should I do? How will edge route to switch 1 know there is switch 2, switch 3? How will each other know each other? And the answer to that is, you have to tell it. In cases where the multicast support is not there, you have to configure what is called as adjacency server. And it's a very scalable, nice solution. What you do is, if I say, for example, I want switch 1 to be the adjacency server, I don't do anything here. But what I will do is, in all other devices, I will go and say, okay, your adjacency server is, what is that? 5.1. And here the adjacency server is 5.1. So what happens now, because multicast is not supported, when ISIS is sending their hello packets, updates and all, they will first give the information to the adjacency server. So now the packets are sent as unicast. So first of all, the OTV, they will give their information to OTV. They'll give the information to the adjacency server. Now, adjacency server is now getting the list of all the neighbors. Okay, sorry, 10.8, right? 10.8 is one, which is contacting me. 7.9 is another, which is contacting me. So what I will do, the adjacency server, it is going to replicate this database to everybody. So it's like an update being sent, right? So everybody now knows through the adjacency server who are all the neighbors participating in the DCI. Okay. Now, once they start getting the list of the adjacencies, list from the adjacency server, the database of all the edges, now what happens? ISIS, instead of sending multicast message, it will send multiple unicast messages. So to 10.8, I will send a hello packet. To 7.9, I will send a hello packet. Similarly, 7.9 will send a unicast hello packet to 5.1, and it will send a unicast to 10.8. So everything is going to be now multiple unicasts. Sometimes we call this as head-end replication. Okay, it's called head-end replication. It's going to do head-end replication. Now, obviously, one important factor to consider is if you have like multiple DCIs, okay, one or two DCIs, one or two layer 2 extension branches, no problems, absolutely no problems with that. Okay, but if you have more than one or two, like 5, 6, 7, so on, it's a lot of traffic you are replicating. So you may be consuming too much of bandwidth on each of the WAN just to send a single update. Instead of using a multicast, you would use unicast. So that's a common problem which you will have. But Cisco says for one or two extensions, no problems. It's not going to be that much effectively disturbing. Okay. So these are the two ways in which ISIS can now discover the neighbors and now form adjacencies and now start updating. Okay, the tough part is over. Now everything is easy. Okay, what happens? The first question is answered. ISIS is there, it will form adjacencies, and you know how the form adjacencies can be formed. Okay. Now, when 10.5 is trying to communicate with 10.6, remember, for the first time I'm trying to communicate. 10.5 trying to communicate to 10.6. The frame comes from 5 to this switch here, maybe switch 11, switch 12, I don't care. Switch 11 does not know where. Switch 11 does not know where 6A is. So what it will do? It will just do flooding. It's the regular switch. So the frame will go to every other part of the network. It will go to the switch. Okay. Now, once it comes to the switch, once it goes through this port, once it comes to the edge device, this is also a switch, right? 1.25 or whatever. Here is the first thing that happens. As soon as I learn a MAC address, 5A, port number 1/25, immediately I will send an ISIS update to my peers, to my neighbors. Wow. This time in fabric path, it was exchanging the switch IDs. Here, it is now exchanging the MAC addresses. So, I mean, this site, they don't even have to, listen carefully, they don't even have to try to communicate to 10.5. They don't have to. Nobody is interested in communicating to 10.5. That's okay.
Okay, but sorry,
Wait a minute. Give me 5 minutes on this. Okay. So 10.7, it doesn't even have to, or 10.7 or anybody here, they don't even have to show interest in 10.5. Doesn't matter. As long as I learn a new MAC address, I will immediately send that information to other edge devices. So now, if I look at the MAC address table, the command is still the same. That's the funny part. Now I will say, okay, 5A is connected to 5.1. This is the guy. This also knows 5A is connected to 5.1. So understand this data plane. Understand this update process. So the switch, this switch or that switch or this switch, anybody, as soon as they learn a MAC address from the local internal interface, as soon as they learn about it, they will send this information to everybody. Wow. Now, previously, when I used to get any new network information, I will send it. I will send that new network with the subnet mask. But now, I send, as soon as I get a MAC address in my MAC table, I send that as an update. That's pretty cool. Okay. So what I am getting here, remember, is an ARP request. 10.5 trying to communicate for the first time to 10.6. So it has sent an ARP request. So ARP is a broadcast. So the source MAC address is 5A, destination is 12Fs. So as soon as I learned the source MAC, my ISIS has sent the update, incremental updates. I sent it immediately. But when I look at the destination is 12Fs. What should I do with it now? Again, depending on whether multicast is supported or not. If multicast is supported, I would send this to this multicast address. I will send it to this multicast address. Source will be 5.1, destination will be whatever, 232.1.5.5, whatever. So now when the frame comes here, they don't even look into this 5A, 12Fs, nothing. They don't see anything. They route the multicast packet. So multicast routing, the packet will be sent to those respective edge devices. But what if the multicast is not there? Again, the same thing. Once the packet comes here, I know this is broadcast message, ARP broadcast. I know that also. Because multicast is not supported, I will send as multiple unicast to these two devices. So I will send two packets now. One packet with the destination of 10.8, one packet with the destination of 7.9. Oops. One packet. There we go. Yeah, one packet with the destination of 7.9. So this is the challenge, if you have too much of ARP flooding or broadcast going on, multiple unicast you will have to send because the provider does not support multicast. But anyways, for 2-3 branches, it's all right. So now you are sending this. See other performance issues or performance benefits. So now you are sending it. So now it is received by 10.5 and 10.8 and 7.9. They receive the packet, they cut the packet out, look into the frame. It's an ARP broadcast. So they will simply flood it to the local LANs. So they will send it here, they will send it here. Remember, I don't know still where 10.6 is. So the frame is sent here. The frame comes to this side and it will also go to this side. It will be flooded to everybody here. And then it will be flooded to everybody here also because it's a broadcast message. Okay. Right. Now, once it is sent as a broadcast message, inevitably that is received by 10.6. Now 10.6 is responding. Now when 10.6 responds, the 10.6 is sending a unicast. Okay. It's sending an ARP unicast. The original source will be 6A. The original destination will be 5A. The frame is sent to this guy. Okay. At this point, this switch, remember, this switch will also learn the source MAC address and the corresponding port number, right? 1/22 or whatever. Why? It's a frame. It's a frame coming from switch 2 to this switch. So I will learn the MAC address of 5A also. So I will directly send it on this side. I don't even flood it anymore. Now when the frame comes here, listen carefully. I have learned a new MAC address and the corresponding port number, maybe 1/35 I would call it. As soon as I learn this new update through ISIS, I'm sending it to all my all my edge devices. So even before my data packet has gone the other side, I already got an update about 6A reachable on 7.9. And see the interesting thing again. None of the systems here are even bothered to talk to 10.5 or 10.6. But still, I already have the information about 6A reachable via 7.9. So it is updated to everybody and everybody maintains these tables. Okay. So now I got the packet, I got the frame. Now I try to go to 5A. And at this point, I know where 5A is. Because I know where 5A is, my frame is 6A source, destination 5A, and my packet is going to be 7.9, the source IP, my own IP address, my join interface, and 5.1 is the destination IP address. When the packet comes here, they don't even care what is inside. It's actually an Ethernet frame. They don't bother. The packet comes here, the routing is done based on the destination IP, 5.1. The packet comes to this, decapsulate. At this point, I already know 5A is connected to 1/25 here, send it. This switch will learn, okay, 6A is connected to 1/24. I will learn it. And I know 5A is connected to this whatever port, I will send it there. Okay. This is how the communication is going to happen. Now wait a minute and listen. Last 1 minute. If, for example, this is the beautiful thing about this OTV solution. If, for example, somebody here, maybe 10.10, wants to communicate to 10.6 for the first time, or maybe somebody here, 10.7, wants to communicate to 10.6, it doesn't matter. The point is this. When 10.10 wants to communicate, in this example, it wants to communicate to 10.6, it will send an ARP. Remember, this switch came to know that this switch came to know about it. That's fine. But I, as a system, I need to know the MAC address. Na? So what I will do, I will send an ARP broadcast. Just like anything. I don't know what technology is running. So I will send an ARP broadcast. Now, when this 10.10 sends an ARP broadcast, which is going to be 10A as the source, 12Fs as the destination, when that frame comes here, because it is 12Fs, it will be flooded to everybody and the switch will send it to everybody. Inevitably, switch 1 will receive. So when it comes here, the switch 1, the OTV edge device, it sees, okay, this is a ARP broadcast coming for 10.5 and I already know 10.5's location. I already know the MAC address of 10.5. So what I will do, instead of sending it as multicast or multiple unicast, I will respond on behalf of the destination. As if 10.6 is responding, I will reply. I will directly reply back. So if you look at it from a real-time perspective, if I learn about that for one time, for one communication, for one ARP, all the other systems, whenever they want to communicate to that destination, I won't propagate the ARP anymore. I will only respond as if the destination is responding. Humongous savings. This in OTV they call as proxy ARP. In OTV we call this as proxy ARP. In other words, proxy ARP is this mechanism in OTV. Yesterday, day before I told you, right? In ACI, the proxy ARP is a different thing. Okay. Here, this is proxy ARP. Now, this is more famously known mechanism. Like, whenever we say proxy ARP on behalf of something, you will give the response. So, this is proxy ARP going on. And for the first time when you are trying to communicate from 10.7 to 10.6 or 10.5, doesn't matter. The site B, this switch 3, this edge device, this already knows the location. So, if at least one frame comes from any of the devices to the edge device, immediately it is going to be updated to all the edge devices. So, they are very well aware of the locations of where is what. Now, I addressed the broadcast traffic with ARP. What if I get unknown unicast traffic? Now, when you saw the fabric path, if I get unknown unicast traffic, it is using the same multi-destination tree like broadcast. We saw that. But what happens here? What happens for some reason, this 10.61, it knows the MAC address of 10.62. It's a very rare thing. Okay. But for some reason, it came to know. However, the key point here is this edge does not know. This edge does not know where 10.62 is. If everything worked according to the basic principles, somebody would have sent in this network or in this network or in any of the network, somebody would have sent a ARP, right, to the 10.62. But very corner case, somehow I came to know 10.62. I know the MAC address also. So now the frame comes to this switch. Now, this time it is not a broadcast. If it is a broadcast, I would have sent it as a using multicast address or multiple unicast. I would have sent it. But now it's a unicast message I'm getting. And I don't know where it is. So what edge devices will do is, if you get an unknown unicast, the packets are simply dropped. No two ways, they will be dropped. Suddenly now we keep asking, okay, what happens in this situation? This itself is a very rare thing, I told you. But let us say that situation is there. Now what happens? Ping from here, huh? Just ping from there. Meaning, just send some traffic so that the switch one will learn about it. as soon as switch 1 learns about it, it will send it in the ISIS update, right? Then everybody will know. So at least one frame, send it to the edge. Then the edge will know about it. Whatever is happening on the internal interface, it's a regular MAC address learning, nothing fancy. As soon as I have the entry in my MAC address table, I will update it. That's the fancy thing. So in a corner case like this, yes, in an unknown unicast, which is by itself a very corner case, packets will be dropped. The solution, make sure the destination whom you are trying to ping sends at least one frame to the edge device. Then it will be updated and everybody, second packet onwards, they will reach. All right. Yes, please, shoot the questions. Yeah.
So for the first time, for every site, there will be multicast and multi-unicast will be happen. And once, for second time, it's not going to happen like that.
Exactly. At least one system tries to communicate. I will be able to learn about it. It's not first time for every system. First time for one system in the network, the whole network, one time. That's it.
Okay.
Okay. Kalyan, in switch 1, I have two downstream switches, okay? And one of the downstream switch, I have a PC 10.10. The other downstream switch, let's say I have switch 1 and get two downstream switches, and each switches I have 10.10 and 10.5. So when I try to communicate 10.10 to 10.5 first time, I don't want to go to S1, right?
How can you avoid it? What do you mean you don't want to go to? Remember what you did. These are all some questions we get. Okay, understand what you are doing. You are making S1, which is already part of the data center 1, and S2, which is already part of the data center 2, to look like a single network. Your goal is that.
Okay.
Your switch 1 is connected, whatever fancy way it is connected, I don't care. It is connected to switch 2. Your goal is to make these two networks, let me draw correctly, these two networks, look like a single network for you. That is what your goal is.
Got it.
Okay, so, and now you're trying to ask me, now you're trying to ask me when 10.5 is here, 10.10 is here, when they are talking to each other, why should it go to switch 1? It will go. What do you mean?
They are in the same LAN. Yeah, same LAN. Okay.
My goal has crossed that. And I wanted to have even switch to get it.
Right. So when I try to ping from 10.6 to 10.5, automatically S2 will know.
Yeah, exactly. S1 will know and then S2 will also know.
Yeah.
Okay. Let me tell you one corner case. Again, this is all corner cases, okay? I think your question is, if, for example, let us take a very, let us take a realistic thing. Okay, maybe you started STP, okay, RSTP or whatever. In RSTP also, there is listening state and learning state, right? 10.7 is there, 10.9 is there. Learning state is there, listening is discarding, but you will learn. So let us say the switches came up. Initially, they both were sending frames. When they both were sending frames, switch 11 learned the MAC address of 1/25, 1/26 on those ports. Once the forwarding comes up, like once the ports are forwarding and all, When 10.7 wants to communicate to 10.9, will switch 1 come to know about it? Yes or no? Did you get my condition?
Forward.
Already these two are learned. They are already in my MAC address table, 10.7 1/25, 10.9 1/26. Already I have learned. Now when 10.7 is trying to communicate to 10.9, like they came into the forwarding, when 10.7 wants to communicate to 10.9, will the frame be sent to or flooded to everybody?
Because I do have already entry, so.
Why are you thinking? You should say. Will I send or not?
I will not flood it.
Very good. Why are you thinking? No, this is all new technology. I don't know what to answer. Huh? No. Yeah, I will not. Yeah, so I will not flood it. I will just send it here. So in that case, switch 1 will not learn. And when switch 1 doesn't learn, it won't send it to S2. So maybe you're trying to ask me this question, this kind of a question.
Yeah. So in this case, what will happen?
That's what. I think this is the way you want to ask the question. Right. So, if this is the case, if somebody here tries to communicate and the packet comes here, I don't know where to send. And I will drop it. This is where you have to understand the basic laws of communication. I gave you a very artificial scenario. How did I give an artificial scenario? It looked very real, very correct, right? It looked, 10.7 I learned it in the learning state, 10.9 I learned it in the learning state, very good, nice. No, I gave you an artificial scenario. Let me explain. When 10.7 really wants to talk to 10.9, it does not know the MAC address of 10.7. If 10.9 wants to talk. If 10.7 wants to talk, it would have sent an ARP request. Because I'm in the learning state, I know these entries. But when 10.7, when the forwarding state comes, the 10.7 still does not know the ARP, right? It still does not know the MAC address of this guy. So what I will do, I will send an ARP. I will continue to send an ARP. And when the switch receives, even though I learn these MAC addresses, I will flood it. Now switch 1 will know.
Yeah, as soon as I send the ARP, anyway, S1 will capture.
So, Kalyan, can we say OTP?
One minute, Deepak. Now I will put another condition. Like, see, I'm cornering myself. Let me say, okay, what if I gave an ARP manual entry? For the sake of argument, I gave an ARP manual entry 9A and I gave a manual entry of 10.7a in these two. Now what will happen? So in the learning, switch learned it seems, which is true, which can happen. And in the ARP cache, manually I gave it seems, which is rare, but let us say I gave. Now, they both will happily talk to each other without telling anybody. Forget switch 1. No other switch will know. Right?
Yes.
Okay. So in this kind of a scenario, you will not have communication because switch 2 does not know, switch 1 does not know. However, let us again get real. This is also faked. This is also manufactured scenario. Let me explain. If this is the case, and if somebody here wants to talk, 10.15 wants to talk, what they will do? They will send an ARP, right?
Yes.
When they send an ARP, I will get to the switch 2. Now, when I get an ARP broadcast, I will send it to everybody. No, I won't stop it there. I am dropping unknown unicast. If I get an ARP broadcast, and if I already don't know where 10.7, 10.9 is, I will send it. And switch 1 will receive the broadcast message and it will send it to everybody. Now they should reply to switch 1, na? Got it?
Yep, got it.
Let me give you the final corner case. Finally, I will corner myself. Okay, what if I also put an ARP cache entry here? Got it? ARP cache for 10.77, I already put it. Now will communication happen? Answer please. Come on.
Just repeat one more time, Kalyan.
Now, on 10.15 also, I gave an ARP cache entry so that this won't make an ARP request. Will now communication happen is my question.
Yes, communication will happen. Yes.
How will it happen? No, it won't happen. Over. Gone case. This guy won't send an ARP. The packet will be unicast. The intermediate switches don't know where it is. So these poor guys, they are regular switches. They will send it to everybody. Switch 2 will receive. This is a OTB switch. So if it gets an unknown unicast, it will drop. How will it send? I won't send. Okay. Now,
And there
see
should
how,
be any mechanism to update.
no mechanism. No mechanism. What mechanism? Please send one frame there, I'm asking. One frame there. Not too much. Just one frame there. See how much I have to do just to stop communication. Okay. I have to put an ARP cache here, it seems. I have to put an ARP cache here and here in the local switch, it seems. To the local systems, it seems. They have to be learned already by the switch in the learning phase, it seems. Under all these manufactured conditions, you will not communicate. You want that or what? Simply do one thing. You put an ARP 10.15 ARP entry, right? Go to 10.16 and ping to 10.9. At least this will send an ARP and you will get it. The ARP will be threaded. One frame I am asking. Are we clear?
Yes, anyway, that will happen in a practical scenario.
Yeah, I mean, whatever I said does not happen at all. Like, never happens. Some sadistic engineer is sitting and doing all these things. Okay, yes.
So, Kalyan,
Yes,
in
please.
case means OTP is only between switch 1 and switch 2 on, we can say, on WAN interface, the outside interface.
Yes, it can be between point to multi-point. That's the reason why I drew 3 branches here. It doesn't have to be point to point. It can be point to multi-point also.
It seems like it is based on the means it has taken from the frame relay concept.
Yes, I thought of saying
By its design, by looking its design.
yeah. I thought of saying DMVPN. That's a more appropriate comparison. But if I say DMVPN, some people may say DMVPN is also taken from frame relay. Okay, so fine.
So OTP. And one more thing. Actually, we enable the IS on these WAN OTV interfaces. We can say. So I believe
you don't even enable ISIS. You enable OTV, it will automatically enable ISIS. Yeah.
Yeah. So we just need to enable OTV.
Right.
So it is it like a fabric path?
Almost. If you look at the fundamental logic, okay, anything, maybe in the future, someday you will learn Lisp also. Fundamental logic is this.
Routing the frame.
Routing the frame.
Okay, so
Fabric path is using switch IDs. OTV is using IP addresses.
IP addresses. So we just need to enable the OTV, and it will means automatically will get enabled ISIS.
Yes.
And Kalyan, eventually we needed any ISP like DCI, like in this case.
I mean, somebody should be there, no? You have to have WAN connection. Yeah, of course.
Of course. So, and there should be, means as you said, internet should might be there, or MPLS.
Anything, yes.
Within DCI environment.
Yes, they could have any kind of technology running there. As long as they can provide me the WAN-to-WAN connectivity, I have no problems.
So it means MPLS would be there in the market.
MPLS will go away. MPLS will go away and will be replaced with SD-WAN. This is what is going to happen. Yeah.
Okay.
MPLS will be replaced with SD-WAN. Now, I want to take back that word. Okay. Even if MPLS is there, SD-WAN is going to conquer the control plane. Let me put it that way. Okay. So nothing hurts if there is this MPLS capable. Nothing hurts if I can label switch the packets. Nothing hurts. It's not a drawback. The problem with MPLS is the other features like traffic engineering or layer 3 VPN connectivities or the BGP adjacency formations, the control plane issues, again, ties back to traffic engineering. These applications of MPLS will be gone. They will be replaced with SD-WAN or OTV, or for example, VPLS is another application of MPLS. They will be removed from of MPLS. Only MPLS will do label switching, that's all. And control plane logic, the other applications will all be taken care by SD-WAN. That's what my prediction of the future is going to be.
Control from control perspective.
Control plane perspective.
Doesn't matter how many routers are there, the single control plane would be there.
Yes.
Okay.
So Kalyan, if we run OTV in our 2 data center, then we would have to dependent on a ISP, right? Like MPLS.
Not at all necessary is the point. Remember, if they support multicast is a little bit advantage. Even if they don't do that, I can run my OTV technology on even internet, I said.
Okay.
It doesn't have to be MPLS. It can be a, I don't know, maybe ATM backbone. It could be a internet backbone. What else can I say? If I say internet, everything comes, right? It could be anything. It doesn't care.
Okay.
All right. Yeah. All right. So yeah. Yeah.
SD-WAN, MPLS is also there?
Not at all. MPLS and SD-WAN they are not at all related to each other. Not at all. Okay. SD-WAN is basically taking out the control plane from your environment. So almost like, I mean, it's a very bad comparison, but I'm just comparing so that you just learned OTV. That's why I'm comparing. Otherwise, it's a very bad comparison. It's almost like the overlay network is here, right? You are creating an overlay network between your 3 branches. Okay? You are connecting overlay network with 3 branches. Underlay, whatever is there, BGP is running, MPLS is running, you don't care, right? The same thing happens with SD-WAN. You don't, today, if I want connection from this branch to that branch, you have to depend on a service provider. Service provider, you should ask, can you give me L3 VPN? Then they will charge so much money from you. And then they will put a tunnel for you, like BGP, VPN exchange they will do. They'll create a route distinguisher, route target. You know that. We did it for 2 customers in our lab. Right? All that will go away. They will do MPLS label switching. Data plane they will run. I will not contact these customers, this service provider for L3 VPN. I will do it on my own. That is what SD-WAN gives me. Control plane is taken completely out of the provider scope. Today, without SD-WAN, I am completely dependent on the service provider for the control plane. They will decide how the packets are routed. They will charge me if I wanted another branch to be extended. But now, no. Give me MPLS connection, give me the branch connections. I will take care of the overlay part. How to route the packets, I will take care of it. Which one is the best path, I will take care of it. Very simple control plane. That's the beauty of SD-WAN. It's not complicated at all. Very simple control plane. And you get all the amazing benefits. Anyway, let us not go there. But you got the point. I hope I answered the question. Yeah.
Yes.
All right. So, yeah. And here is the last point. Just like I gave the last point for Fabric Path, OTV, it is Cisco proprietary, almost like this Fabric Path. It is not supported by all models also. It is not supported by all Nexus boxes. Currently only 7K support. I am not 100% sure at this point 9K support. I doubt it. Okay. But 7Ks are the only ones that will support OT. Okay. Now again there is a proprietary lock. Okay. So tomorrow, on Monday, we will be talking about this thing called VXLAN. And the beauty of this is, it will literally like consume Fabric Path and consume OT. It took the both concept and put it into one big technology. Very nice. Meaning, I can use VXLAN within the data center. I can also use the same VXLAN technology for my DCI interconnects. Even more interesting, VXLAN is supported by all the vendors. It's an open standard. So, my take, you will not see OT. You will not see Fabric Path. You will only see VXLAN in the future. Okay. So more on that VXLAN we will be discussing on Monday. Okay. I am thinking Monday we will finish it before lunch, I guess, but let us see. Okay. So with that said, anything I want to cover in OTV? I think I will draw the line here. And from a configuration perspective, you will have to, just like Fabric Path, right? By default, the VLANs are not allowed. You have to configure the VLAN mode as Fabric Path. Similarly, for the OTV also, whatever VLANs, remember the 10.x will be in some VLAN, right? So whatever VLANs you want to extend, you have to tell that. You have to extend those VLANs one by one. So it's not like for every VLAN you will have, once you enable OTV, all the VLANs will work like this. On a VLAN by VLAN basis, you have the flexibility of making them extend. So that is one thing you do. And one other thing I want to say very quickly, I will say multicast. Okay, broadcast unique, unknown unicast. We saw how that works. A multicast, they will create another data plane multicast group. Again, this is only when you have multicast support. If you have multicast support, then what they do is, For every multicast application, so there may be some multicast application going on. So that is what they call inner group ID. Inner group ID. So for every multicast application, for the service provider, they will map it to a outer group ID. Okay. Outer group ID they will add. So they will do a one-to-one mapping of the multicast addresses from the inner actual application group multicast and the multicast address given by the service provider. So with that, those who are having the receivers, they will send their IGMP joins. You will send the IGMP join on this side. So only those in that multicast group will receive that multicast tree. So you may need it when you look at some configurations. You may see the data plane multicast is used for the multicast traffic flows. The control plane multicast is something which I use if, again, multicast is supported for ISIS. But if multicast is not even supported, then adjacency server will be configured and multiple unicast will be sent. So, yeah. All right. So with that, I would like to draw the line here for the day. And, okay.